the man himself here. And the blue jacket, if you don't recognize him, Jens is turning 60 this year, next month. Jens was my advisor for my PhD. I thought I owed him some payback in embarrassing him. I won't say too many embarrassing anecdotes, but I will in my talk, don't worry. But actually, the real welcome is going to be done by Todd, who's known Jens since at least 2004 when you joined UCLA. But we've got a great selection of talks. It's mostly former students and former colleagues. And we've even got Jens's advisor here. So Peter Mosses is here, sitting right behind him. I had actually not met Peter until this morning, other than over email. And so for all of Jens's students, that's like your grandfather. So get a chance to talk to Peter. It'll be wonderful. So without further ado, Todd.
Is my mic working?
I think so. Is it?
You have to stand a little bit.
Is it working?
Yeah, now.
Okay. Cool. Okay. Well, I'm really happy to be welcoming everyone here today and sharing my experiences and honoring one of my favorite people, Jens Palsberg, sitting right over there. I'm lucky enough, as Ben said, to have been Jens's colleague for the last 20 years, and I've known him longer than that. And I'm calling him three of a kind because he gets so much done that I'm convinced there are three of him. So, everybody knows Jens. He's, there's one sitting right here, but I'm pretty sure there's another one right now in an important meeting somewhere. And there's another one writing a letter for someone's award somewhere as well. So, Jens does so much it really boggles the mind. And you may think it's far-fetched that there's three of them, but he moved to quantum computing a few years ago. So who knows? Who knows? But the reason I'm also calling him three of a kind is because I think he's played kind of three distinct roles in my career since I joined UCLA, and I kind of wanted to highlight those. So one is as a mentor. When I joined UCLA, well, actually, first of all, even before I joined UCLA, I knew Jens when I was a grad student because he was colleagues with my advisor, and I went to interview at Purdue, and he was there, and as I recall, he met me for dinner the night before and said, "Hey, they may be going to hire you as my replacement. I'm leaving," and so he's moving to UCLA, and then I got an interview at UCLA, and so then I interviewed there, and he wasn't there yet, but I knew he was coming, and so moving to UCLA Jens was like a big draw for me there, and once I moved there, he really kind of helped to mentor me as a new professor in many different ways. We wrote my first grant proposal that I ever wrote was with Jens. That's a little small, but Jens was the PI on a grant we wrote right when I joined with two other colleagues who had just joined, Eddie and Rupak. That was a successful grant, so that was my first grant proposal. We worked together on research. Early on, I had this project on type qualifiers and wanted to do type inference, which I didn't know anything about. Of course, Jens is an expert in that area, constraint-based type inference, and so we worked on that together. He involved me in various projects, like writing a chapter of a textbook. I also taught his course a couple of times, and that was really eye-opening because he has this course that he's still teaching today that in 10 weeks takes students from a high-level language, from a decent subset of Java down to assembly, and I really learned a lot through that course about challenging students and that they'll rise to the challenge if you give them support to do that, and that's really informed a lot of my teaching, and I've gone on to kind of create courses that have that same philosophy. So really kind of formative experiences in the first 3-4 years that I joined UCLA. The next Jens number 2 is the citizen, and Jens is really a model citizen, as everybody knows, kind of in the department, in the broader university, in SIGPLAN, in ACM. It's kind of crazy. I took this snapshot of Jens's CV a couple days ago. I think he's the only one I know who has 13 pages of his CV just for his service record. And actually, I'm pretty sure that the table of contents goes to the next page, so I didn't quite finish the entire service thing. But I was looking at it, and it's actually staggering. If you just look at the service to UCLA, he was the department chair for 5 years. He was the vice chair for, I think, 2 years or so. And as far as I can count, he was the head of the faculty hiring committee for 8 years. So that's 15 years out of the 20 years that he's been at UCLA. He's been doing one of the major service roles in the department. And that's only the department. And then if you know Jens, you know that out in SIGPLAN, in ACM, actually now at UCLA at the campus level, what I just said, that's 4.3 service to UCLA. but there's all these 4-point other things that are everything else. So it's really mind-boggling, and you know, that's been a big he's played a kind of a role as a role model for me to kind of understand the importance of being a good citizen, and also the impact you can have by playing those roles. And so right now I'm the department chair, and you know, Jens is really the person that I rely on the most for wisdom and advice and feedback. And you know, if I ask him a question, he's usually available to give me a call, you know, within an hour or two and tell me some experience, some story about something that happened in the past, and you know, some sage wisdom on how I should proceed. The last one is Jens the Explorer. So I think Jens is also a model of how to have a fulfilling career as an academic. You know, he was 5 years as the chair, and he could have just very easily gone back to doing what he was doing before, which was, you know, static analysis and compilers and you know, the traditional stuff he was doing, and that would have been great, and that would have been very normal. But really, he took a left turn. Actually, he took kind of 2 left turns. You know, he took a left turn into getting an MBA, and then after that, he took a left turn in terms of quantum, and of course, still using and leveraging the things that he knows well, like programming languages and static analysis, but really jumped in this new area, jumped into the unknown, kind of challenging himself, forcing himself to learn new things. And I think that's been very inspiring for me, and I think it helps me to make bolder choices in my career. There's a 4th bonus Jens, which is the comedian, which is Jens is one of the funniest people I know. Hopefully other people, I think Krishna is collecting stories, so hopefully Krishna will say something good about that. And that's really all I want to say. I want to thank all 3 Jenses for the role that they've played in my career, and I'm sure in many others sitting here today. And welcome again. I'm excited to be here.
So the first one is going to be Julia. She's going to talk about Coccinelle, that's how you say it, right?
No,
Program transformation in the
you
real
don't have
world.
a USB-C?
And I will actually embarrass Jens once more. So Jens' quote from roughly 2002, there's a fine line between meanness and evilry. Meanness is for the midterm, evilry is for the final.
Nothing is happening.
It's not a, is it good? Yeah, it's just a splash, so it's not really showing up yet.
Okay.
But it should be fine. So yeah, it's just showing.
I see this one. Sorry, is there going to be the splash thing always in
I
the
don't
corner?
know. It's open. It's wait. It should be up now.
Okay. No, it goes away every time.
It's working now.
Okay, but still, can you get rid of the splash thing on the screen?
Oh. Oh, it's good.
No, it's gone.
Yeah.
Now it's here. Now it's gone. Okay, thanks. Okay, so thank you. So I'm going. My name is Julia Lawal. I'm a researcher at INRIA in Paris. My main interaction with Jens was quite a long time ago, actually. It's surprising how fast the time has gone. So in the mid-1990s, we were both postdocs in Boston, and I have also had the chance to discuss with him at various times in the future. And so this talk is sort of about how he has contributed to my view of research. So yes, in the beginning, I was a postdoc at Brandeis, and Jens was a postdoc at Northeastern. And at that time, the thing to do if you were interested in programming languages in the Boston area was to attend the, I think it was every Wednesday, the seminar at Northeastern that was organized by Mitch Wand, where we had the presentation of a paper, and we afterwards enjoyed a discussion and some food. There was like some Middle Eastern food truck. I enjoyed baba ganoush, not exactly in this format, but it was the best picture I could find. At the time, Jens was working on this paper that impressed me a great deal about the type system equivalent to flow analysis. I very much appreciated the idea of thinking about something. I mean, we've got these two things, type systems and flow analysis. We kind of familiar with them, take for granted how they are, but it seemed like an interesting idea to think about them deeply and try to understand what the connections were between them. So moving forward, a little bit of time went by. Actually, Jens went back to Denmark for a little while. And then a bit after that, I left Boston for a postdoc in Rennes. Coincidentally, Jens came back at the same time, and as I left, and I dumped my apartment and all my furniture on.
We still have some of it in the house.
Okay.
Most of each.
Okay, that's good. Some of it was nice, some of it was not so nice. I mean,
some of it was very nice.
it was grad student furniture collected from other people's yard sales, but some of it was nice. Anyway, so I was a postdoc in Rennes in France working on partial evaluation. I'll talk a little bit about partial evaluation now. Partial evaluation is something that it's a program transformation approach. It aims to fully automatically optimize some source code with respect to some of its inputs. So in a very brief example, this is quite a classical example. We have an interpreter for an expression, takes expression and environment, and then it just figures out what to do for additions and figures out what to do for variable references. And so if we want to evaluate this interpreter, we evaluate the interpreter with respect to some appropriate arguments. We have an addition expression. It has a variable x and a variable y. And then we also have an environment. This is mapping those variables to their values. So this is all written in Scheme. Scheme is actually a language I have not used in the last 20 years, but it's quite funny. I actually had to ask my PhD student to translate some ML code into Scheme using ChatGPT to generate this. But it's in Scheme because partial evaluation at the time was quite focused on Scheme. Scheme is a language that's easy to manipulate, easy to generate code that can be executed, and so on. So basically, here our idea is we're going to evaluate this expression with respect to this environment. We start out with our add. We see add here. Now we need to sum up the interpretation of those two sub-expressions. Now we have var x, which will be one of our expressions. A soak is the Scheme way of looking around in a list to finding the value that's associated with a key. And so we'll find the value 3, we'll find the value 4 here, and then we'll add them together, and we'll get 7 as the result. So not very surprising. That's normal evaluation. Then we have partial evaluation. Partial evaluation is kind of the same thing, but we don't have all the inputs. So the idea is you have only part of the inputs, and you try to optimize fully automatically the program as much as you can based on the information you have available. So the typical case is we partial evaluate an interpreter. We have an expression, and then we don't have our environment. We just have a representation that indicates what information we have. It's this called static, and so we have a S for the first argument, and D, this is the unknown thing, indicating that the environment is not known. And so then it's kind of like evaluation. We just kind of do our evaluation stuff, but we just stop when we don't know what to do next. So here we're doing partial evaluation of our interpreter. We have add expression, and so now we have enough information to be able to simplify the add expression, and so we can figure out that we need to work on this. And now we will work on var x as E1 and var y as E2, and we have actually the same pattern of execution as we had in our original call. We have our expression, we don't have our environment, and so we can try to push things forward with respect to that information. For example, for var x, we will come down here. Now this x is the string x. And then the evaluation is going to be to try to do this ASOC. But ASOC requires looking around in the environment. And since we don't have the environment, we obviously can't do that. And so now this is where we're different from evaluation. We have to actually reconstruct the term. So we'll reconstruct this ASOC xenv. We'll reconstruct ASOC yenv as the result of this interp here. Now we have addition. It's got 2 arguments. We don't know what they are either, so we need to reconstruct that. And so we produced this specialized program that is, in principle, much faster than the original one, and has fully taken advantage of our addition expression, and it just left over the things that depend on the environment. So this seems very nice. It looks like it did something. So this is something that was studied quite a bit in the University of Copenhagen and also in the team in Rennes that I joined. Basically giving partial information about a function's inputs, partial evaluation is going to fully automatically produce a function that's specialized to these inputs. On the other hand, people using this kind of found some difficulties. One of them is that this whole process requires access to the full source code. This is a source-to-source transformation. We're analyzing the source code. We need the source code to do something with that. But if you think about scaling up to real applications, for example, are going to have libraries. We don't necessarily have the access to the source code. So then what do we do in that case? And the other big problem that came up is that we have this known information and the unknown information, and sometimes some computations can involve mixing the unknown and known information, and then we don't really know what to do next. So we already saw that in the case of ASOC. That was kind of expected. But in many other applications, it was found that the propagation of your known information could get blocked by some interactions with the unknown information. So this sparked an entire industry of doing what were called binding time improvements, figuring out how to kind of isolate all the known information and keep it separated from the unknown information. One would have to, it was supposed to be a fully automatic transformation, but one would have to do a lot of preparation of the source code to get that fully automation to work out. So partial evaluation had been going on for a certain amount of time. And in 1998 in the University of Copenhagen, there was a summer school on partial evaluation practice in theory. And I attended that, and Jens attended that also. And at some point, for some reason, we had the occasion to walk around these very nice lakes that are around the center of Copenhagen and kind of chat about the future of partial evaluation and where this was all was going and so on. So basically, the concern was how can partial evaluation make the jump from the toy example, like I showed, to doing something applicable in practice. And so there was kind of a first step in this direction that was made both at the University of Copenhagen and at the team that I was working with in Rennes, which is to do, instead of doing partial evaluation of scheme, to do partial evaluation of C. So there's a CMix at DIKU in Copenhagen and Tempo in our team. But this was kind of, if you build it, they will come or something. It wasn't really clear what was going to happen after actually developing these tools. And we come back to these issues that I highlighted before. We still need this full source code. As we're all familiar with, C code has lots more library uses. malloc, you don't want to know what's going on under there. So the partial evaluator cannot be analyzing the implementation of malloc, but on the other hand, it has to know what to do when it comes to a malloc or printf or sign or any kinds of library functions. Some of them it should be unfolding if it knows all the information, and some of it should not because they have some kind of side effects that needs to be preserved for the specialized program. So in Rennes, in Tempo, they came up with some kind of interface file where they have some kind of simplified definition of these kinds of library functions. I remember Jens thinking that was kind of a good idea. One could think about what kind of analysis you could do with respect to these interfaces and so on. And of course, there was also this issue of binding time improvements. In Rennes, there was something called specialization classes where we tried to think about like good patterns of specialization programs that would work well with partial evaluation, and then developers could perhaps take those patterns and compare them to their own source code and see if they could do something. So there were different efforts to try to improve the situation, try to bridge this gap. But over some time, I think the level of enthusiasm kind of dimmed a little bit. And I think at least from my point of view or from the point of view of some of the people around me, the problem seemed to be this idea of full automation. Automation is the idea of you're supposed to give the partial evaluator a couple values, and it's supposed to do miracles in improving even maybe the complexity of your program. So all this full automation is alluring, but in practice, maybe predictability is the key to usability. You want if your developers are really going to use their tool, they have to somehow know what to expect. And so the rest of this talk is actually not related to Jens in any way, but it's sort of informed based on this discussion that we had in Copenhagen, different interactions, with this goal of how can we do interesting things with programming, program transformation, programming language concepts that will actually have some impact on real developers. So in 2004, I was on sabbatical in France. I worked with Gilles Muller, who also actually had invested a lot in partial evaluation, in actually trying to apply it on real code, sometimes with good results, but good results after a huge amount of perhaps difficult effort. And so the problem that we targeted was how can we maintain software at a large scale? So for some kinds of software development problems, the developers know what they want to do. They know what kind of code they want to change. They know what kind of changes they want to make. And all they need is help in navigating all the code and making those changes in a reliable, comprehensive sort of way. So we focused on the Linux kernel. Linux kernel at the time we started was 4 million lines of code. Today it's 26 million lines, almost 26 million lines of code. It's still rapidly growing. It also incurs frequent changes to improve performance and to prove correctness, fix bugs, provide new features, and so on. It's kind of an endless problem to keep it up to date. And so the question then is how to perform evolutions in such a large code base. And so in thinking about it, we tried to, well, I mean, our goal was somehow to provide something that was like sound and meaningful and would do proper things, but also something that would be accessible to the developers that we were targeting, who we hoped would actually use the tool that we were considering to develop and use it enjoyably, not with great deals of frustration. So an insight was that somehow patches are the key to reasoning about change in the context of the Linux kernel. So a patch is just a description. It's just a small fragment of code. We're going to remove, it has just a few annotations. We'd like to remove some lines. We'd like to add some lines. It's a very simple concept. It can be created automatically if you have the old version and the new version. It's the way that developers communicate about their changes. Somebody is making some change. Maybe they would like feedback from someone else, some kind of code review. They can send the patch. The other person can see how things were before, how they're going to be now, and so then they can make a proper assessment of what's going on. On the other hand, patches are not very good for what our ultimate goal was, which was to be able to make changes at large scale, because a patch is going to specify, I cut it off here, but it specifies exactly what file is going to be affected. It's going to specify exactly what line numbers are going to be affected. It specifies some neighboring lines. It has some variable names here and stuff like that that might not actually be relevant to what we want to do. So the patch idea is good from coming towards the competences of the developer, but it's not really good for doing things at a very large scale. So just to comment on what we're trying to do here, this kmalloc is the Linux kernel's internal memory allocation function. Memset is just like it is at user level. We have a region of memory where I want to put zeros everywhere. So the idea here is that we allocate some memory and then we zero it. And this is 2 lines of code when we could just write it in 1 line, because there's this magic function called kzalloc that will do both of those things at once. So it's a very simple change. We just want to change 1 letter here from M to Z, and we just want to remove this line. It's like 20 keystrokes or something like that. But this is actually quite a hard thing to do at scale, because there are actually many calls to kmalloc, and they're not actually all next to memsets. There are many calls to memset. They're not actually all next to kmallocs. And the distance between them here, it's about 5 lines, but it could be larger or smaller distance, and so on. So it's hard to actually scan your code base and find all the opportunities. So basically, our idea was to take these patches that everybody's familiar with and somehow raise the level of abstraction. So what we do is we basically we introduce meta variables, variables that are going to represent any arbitrary expression. And so that's here, this transformation doesn't really depend on what these two values are, so we can just put some random meta variable there. On the other hand, the transformation does require this to be a 0, so then we can put a real value. So we can just freely mix the things that look like ordinary source code and things that make the transformation more abstract. We also have this ... operator. It's like, the idea is like if you're talking with your colleague, you want to describe what you should do, maybe you're at lunch, you write it on a napkin. This is supposed to be something that's like what you would write. And so you can take this rule and you can apply it across the Linux kernel, and then you get rid of all your kmallocs and memsets and turn them into kzlx, and then your code is a little bit shorter. So this, we published the original idea in 2008 at Eurosys at a systems conference because we're targeting Linux kernel. But on the other hand, we are somehow designing a new programming language, and all these operators and meta variables and everything, they actually have a precise semantics that we actually hope our users don't think terribly much about. We kind of hope that this chosen semantics is what they expect it should mean. Maybe that doesn't work 100% of the time. But we worked out all the semantics, and so that led to a paper at POPL. And then here's a retrospective paper that kind of reflects on the lessons learned about 10 years later. So we can go back, we can look at our tool in terms of the two criteria, automation and predictability. So we've definitely sacrificed in terms of automation. We don't just like say, I do this, it just should happen all by itself. You have to actually script everything you want to do. Sometimes there are multiple cases that you need to take into account, and you need to actually script all those different cases. On the other hand, the actual transformation part is fully automatic. It goes around and finds all the relevant files. It updates them all in a nice way. It makes a patch for you. You can send it off to whoever is going to review it, and so on. But we've made a huge benefit in terms of predictability, since we are basically making a programming language for writing transformations. It's a deterministic programming language. It kind of just does what you tell it to do. So users in general are satisfied with the results that they get out the other side. Sometimes it's necessary to refine it. You might not have taken some issue into account. But again, also since it's very much based on the source code itself, it's easy to modify the specifications to improve them in some way. So the kind of goal, the original goal was that actually other people should be using the tool. So we can ask, did it actually work? So this is the use of Coccinelle. These are like commits in the Linux kernel that mention Coccinelle. So there are over 11,000 of them. The blue ones are made by the Coccinelle developers, so we had to do some work to actually get the idea out there in the community. And the pink ones are done by other people. You can see here it's kind of declining a bit over time in the recent years. But on the other hand, Coccinelle is in various continuous integration tools of the Linux kernel. And we're also in touch with other people who are using it for various things where they use it maybe more for exploration and for prototyping things. But the actual transformations they do are very kind of specific, and so they don't necessarily always mention Coccinelle when they have used it at some point in their development process. So in conclusion, Coccinelle is a user-friendly tool for updating C code at large scale, inspired by developer needs and expertise. Over 11,000 patches. It's been kind of growing continuously over the years. It allows developers to react quickly to changes in the code base. So if you're not using Coccinelle, the kind of standard thing to do is like make a temporary version of the new function, and then you've got a few of them updated, and then you hope that other people will take care of it over time. With Coccinelle, you can sweep over the code base and do the whole thing. And this whole work kind of follows a bit the inspiration from Jens, which is it's interesting to think about things that are interesting from a programming language's point of view, but that can actually also have an impact in the real world. So everything is available. So thank you very much. And thank you, Jens, for all the discussions at various times over the years.
I will grab the mic. Julia, it's wonderful to see how Coccinelle has been so successful. I remember thinking that it must have been a big jump when you kind of moved from Scheme to C. And it was just so successful. It's really great to see. We actually have a lot of your furniture still. I took it with me from Boston to Indiana, and then from Indiana from house 1 to house 2 to house 3, and now to Hermosa Beach. If you can ever come down and visit, you will see that it's still there. It's still good stuff. But anyway, yeah, it's been great.
My computer just before the presentation.
All these years, it's just wonderful that you are the one keeping Linux going.
So in your example with the transformation that had ... I mean, that transformation is not valid unless you have some constraint on what happens in ...
Yeah, so this was a short talk, so I didn't go into all the details. But on the ... you can put a when, and you can say when certain things should not appear in that place, and then you can actually make it safe, yeah.
It's a bit low.
Any other comments, questions? Okay, thank you.
Well, not for me. It's okay, don't worry.
All right, so we got another talk. So just a testament to the breadth of people that Jens has advised. Christian has worked a lot on cryptography and peer-to-peer networking. And so Christian was Jens's PhD student. He also worked with Jan and graduated from UCLA in 2006. So take it away.
Thank you, Ben. Yeah, so again, this is, as Ben said, to show the breadth of Jens's interests in part. And I had, in my PhD times with him, 2 interests in programming language, obviously, and security, and he has always encouraged both. So he now has to suffer through a security talk. And now I know why the clicker didn't work. Okay, so because I'm not speaking to security audience, I want to introduce the people that are going to be starring in our play. And first of all, we're going to have the Walters. Usually you know about Alice and Bob. We're talking about the Walters. Walters are people we trust a little bit, right? And they sign some kind of messages, and they are helping us in the protocol, right? So that's also Walters. They have their own signing keys and they sign messages. And then we have Peggy, and she wants to convince somebody of something. She's the prover. She tries to prove something to some person, right? That's Peggy. And one example that is quite common, and that has kind of been the motivation for the original work here, was that there's this web of trust where you try to prove that somebody has this PGP key, right? So Peggy has some PGP key, and the Walters have witnessed that, have met her, and can say, okay, this is actually Peggy's key. I've checked, I've met her. She's shown me her passport. And so Peggy wants to convince some other person that she hasn't met in person directly that this is really her key, right? And this person is Victor. He's the one who tries to verify that whatever information Peggy has, that the Walters have presumably witnessed. Okay, that's our setup. So the goal is basically, so we have a couple of people that are trusted by Victor. So some Walters are trusted, right? Not everybody in the world is trusted to validate information. And on the other hand, of course, some people have actually witnessed the thing, the key association or the event. And so they have provided Peggy with that signature. And what we want to find out is, what is that intersection? And we want to see how big is the intersection, because if there's only one person, well, maybe that's an attacker and it's bad, but if there's 50 people in the intersection, that's great. So we want to compute the set size intersection of the people that are trusted by Victor and the people that have actually witnessed the statement that Peggy wants to prove. Okay? Pretty easy. Now, the problem is, well, these are basically social relationships, and we don't necessarily like to have all of the information out there. You don't want to disclose exactly who you are trusting. And if it's depending on what it was, maybe you don't want to disclose who has witnessed the event. So, but we want to see the intersection. Right? So we have a privacy problem here. And that was the goal of the fork of trust protocol, was to basically go and say, okay, the specific statement, yeah, that can be public, but we don't want to trust who signed it. We don't want to trust, the other party doesn't want to trust who they trust. And we want to get the size of the intersection. Okay, so the fork of trust protocol is therefore the idea of a machine that is, as a machine trusted by Peggy and Victor, or we could say a cryptographic protocol, of course, that converts the valid signatures and the public keys into something equivalent that we can't get back to the original information, but we can use to compute the set size intersection. And I'm going to present a slightly simplified version of the original fork of trust protocol. It had some additional steps in there, which in the end turned out to not matter. They helped defend against some problems, but they didn't, well, achieve the big goal, as we will see. So that's the idea. We will build this fork of trust machine that takes the keys of the people we trust, the signatures, and then we produce something that is equivalent, where we can still check the signatures and so on, but we can't get back to the entities that made the signatures. Okay, and then we can, of course, build trust without disclosing the private information about the Walters. Yeah, so that was the goal. How did the fork of trust protocol work? Well, first step is Victor randomly blinds the set of the trusted public keys he has and gives them to Peggy. Right? So we take the keys we have, we blind them, so Peggy can't get back to it. It's an isomorphism, which means even if she had infinite computing power, she couldn't compute back the original one set, and we give that to Peggy. And then Peggy takes her messages and the signatures and the blinding public keys and blinds everything again with her blinding factor. Right? So it's like double crossing everything. And yeah, she might also permutate the order and stuff like that, details. So it's sets, not arrays, where we can say, oh, 5th position, that's this one. Right? And if we don't want to disclose the size of the sets, we could also pad them with random things. Right? So we could just add random people we trust, and they don't really exist. We just made up some public keys or something like that. Okay, so we send that back to Victor, and then basically in a bit of the style of Diffie-Hellman, well, first of all, Victor checks the signatures, and then for the things that Peggy gave her black, well, they were not blinded with his blinding factor yet, so he blinds them again. Right, so now everything has been double blinded, and we can basically see, well, it's double blinded. Well, how big is the intersection of the double blinded information? That's the high-level idea of the protocol. Okay, so now given that we had this JENSFEST coming up, I told his future grandchild that I would want to have a formal verification of this protocol. Let's prove that this is actually correct. And we thought the difficulty was going to be to precisely formulate the privacy properties, given that we still reveal the set size intersection and that there's this padding problem and how big are the sets. And so, yeah, well, as in some sense, some of the most interesting working type theory is not proving a type system sound, but proving it unsound. Same thing applies in security. If you try to prove the security protocol correct and you find out, it's also a very good lesson. And paper was published by Garcia like 7 years earlier. Nobody found the problem. Nobody bothered formally verifying it either. So, okay. So instead of a proof, you get a disproof, right? Okay, so how does the attack, well, we have two attacks. How does the first attack work? Well, we first want to find out who are the people, who are the Walters that signed the statement on Peggy's side. And so the first thing is of course, Victor cheats. And he doesn't blind everything the same way. He just uses a different blinding factor for every one of the keys. Right? So poor Peggy, of course, follows the protocol, right? Sends back the double-blinded information. And then what our attacker does is simply, okay, now he has to blind everything with all of the blinding factors he used. And if he finds a match, then he can go and say, well, that one had to be this one in my original set. And given that these are isomorphisms over very, very large groups, think 2 to the 250 elements, something like that, it's basically, if there is a match, well, he can be very, very certain that this is the right one. Right? And so thereby, he can basically follow back the chain and say, okay, this is one of the people who signed it. And so as long as he has an idea, oh, I suspect maybe this Dennis guy, he was the signer, he puts him in his set as trusted, blinds him in a specific way, and if it comes back and after, unblinding on vectors, there is a match on this with this particular unlinked vector, he knows it was Dennis. Okay. So we said, okay, well, that's bad, but maybe it's only half bad because at least whoever Victor trusts is still protected. Okay. Second attack. We want to find out who Victor trusts. This one is a bit more specific. The fork-off trust protocol was instantiated using BLS signatures. And it's the only instantiation we know of, so we have to go a little bit into detail of how the cryptography worked here. And, a bit unusual, it requires actually that the Walters collaborate with Peggy against Victor. Right, so it's usually thinking of different entities, but of course in a security analysis, you can't just say, nobody collaborates against, And so the situation is basically, you want to find out, Dennis wants to find out, does Jens trust me? Am I in his set of trusted things? I'm going to have Jens run this protocol with Christian, and we're going to find out if I'm in his set. So I'm happy to work with Christian against Jens. That's the idea here, right? Collaboration. Okay, I have to give you a brief introduction on BLS signatures. Who here knows already BLS signatures? Oh my goodness. Well, fortunately, in my view, it's the simplest signature scheme we have if you look high level at the theory. It's the worst to implement, but from the theory, it's actually the simplest one. So I tell my students in crypto exams, if the examiner asks you, give me, explain to me some signature scheme, always use BLS, right? Okay, so what do we need? We need a multiplicative group of some prime order P. I always have some groups. And there has to be some generator we've all agreed on. Let's call it gamma. Have some hash function that hashes elements into that group. And the complicated thing is we need a non-degenerative bilinear map. Non-generative or non-trivial means not everything is mapped to 1, or the neutral element. And it's bilinear, which means we have 2 arguments, and basically it's multiplicative in both, so we can pull the exponents out. Those things exist. If you implement them on top of elliptic curves, the implementations get horrible, evaluating E is expensive, but we can believe, okay, these kind of things exist. So, now, we take a scalar, just a number modulo P, that's our private key. The corresponding public key is the generator to the power of X. Also easy, right? And then the signature, if we want to sign a message, well, we hash the message to the group, and then raise it to our private key. Well, very easy signing. And if you want to check whether a signature is valid, well, we take the signature and the generator, evaluate it under the bilinear map, and check if that's the same as if we take the hash of the message and the public key under the bilinear map. And if you just fill in the equations I put on top and pull out the exponents, you'll see that those two things should be the same. And if you then take a DDH assumption on the groups, you can find out that, okay, it would be difficult to produce one of those if you don't have the private key. Okay, so why are BLS signatures fun? Well, we can use them for blinding. So if we have the situation where we have a private key X and a signature, and we take us a blinding factor B, again modulo P, what we can do is we can basically raise our public key to the B and raise a signature to the B, and it will still match, because it's bilinear. So we can blind the public key, get a new public key, and it's clearly a discrete logarithm problem to go back. And we can take a signature, raise it to the same blinding factor, and the signature will still sign the message for the blinded public key. Oh. Okay, so now how does this help us find out who Victor trusts? Well, let's assume that Victor has a set of people they trust, and he has picked some blinding factor that he's going to use to blind it, and so he's going to send out as the blinded set to Peggy, the public keys of the people he trusts raised to the B. And again, here we assume that the victor is the honest guy, right? He's just following the protocol. He's not trying to attack us by picking different blinding factors. Okay, so now what we assume is the interesting assumption, well, Peggy has access to the private keys of the Walters. After all, they are conspiring, right? So now, what can she do? Well, she can basically, if you have a private key, there's a group. Group has a group order, which means there's an inverse. She can compute the inverse of the private key and multiply everything she gets from Victor with the inverse of the private keys. And if they match, it basically gives her gamma to the blinding factor. And then she can go and say, those two match, and I get this gamma to the blinding factor. And now I can, of course, just iterate. I have determined the blinding factor. I can raise gamma to the B. Well, I haven't determined B. I've determined gamma to the B. But I can raise that to the private keys, and I'll find all the people that I've conspired with, whether they are in the set. Right? The only prerequisite I had is that basically 2 of the people that were trusted by Victor were in conspiration with Victor. And then it's completely game over. Okay, so to conclude, first of all, the protocol has fatal flaws that we don't really know how to fix. Right? So it's supposed to protect privacy, and on either side we can break it. In one case with a bit of stronger assumptions, but that's still too bad. Second part is, well, this was very useful to attempt formal verification. So thank you, Jens, for breaking yet another protocol. So it's actually useful to do this stuff. And overall, I would say one conclusion is we need to keep a very open mind on adversarial capabilities. The idea of, Victor conspiring with the Walters and them handing out the private keys, yeah, this is fun. And we've seen before in the literature some other papers where they were doing some privacy protocols, triple Diffie-Hellman, and where also, if this privacy key is compromised, which wasn't exactly in the original people's mindset, then very, very bad things can happen. Right? And so keep an open mind on this. We actually also saw something similar with TLS. You all know about TLS at least, right? So TLS 1.3 was developed with formal proofs, and they really went and said, okay, we have first version of TLS that has a formal proof in it, and then a couple of months later, and I always told my students, well, be careful, formal proofs is great, right? But you can't be sure that that's everything, right? And a couple of months later, a paper came out basically saying attack on TLS 1.3, and what they had done is they had used an attack that wasn't covered by the formal proofs. It wasn't covered by the adversary mod. Yay. Right, so formal proofs, great, but make sure you prove the right thing. Thank you.
I just want to say, I think it's wonderful that you're putting out an open problem for the whole crypto community. So I love these hard open problems. I think that you will find a whole community out there who will go off. So who was the list of original authors we can thank for this fog of trust?
Garcia, Burgess,
yeah,
and me, actually.
Yes.
Oh.
Yes.
But the thing is, yeah.
So this is great. So I think that this is something people know about. Now it's instead of being something the community can trust, now instead it's an open problem. So this is yeah.
Could the next speaker also come up and get ready? Jack.
Yes.
So the next talk we're going to have is entitled MiniJava on RISC-V, a game of global compilers domination, which sounds like a lot of fun to me. I like compilers. And it's 2 PhD students from Marquette. So these are your grandkids, Jens.
Sure. All right. do anything to transfer it over? Oh, got it.
Do you have the presentation mode on? Presenter mode on?
Do you want me to grab my Mac?
I think it should be fine. Here we go. Yeah, it's mirrored. Okay, mirror works, yeah. If you have, it should probably be changes. Okay. Can you see it now?
All right. Hello, everybody. My name is Jack Forden. I'm joined by Alex Gebhard. In the audience, we have Maverick and Dennis Brylo, and we're going to be walking through MiniJava on RISC-V, a game of global compilers domination, which sounds perhaps a lot more foreboding than it actually is. So the outline that we're going to be walking through are really our problems and motivation sets for building a new pipeline of upper division courses at our institution and at others, and then the related work that we found or really haven't found in the field in this area, and then building the platforms to actually support more than just a single course, but actually a suite of courses. And then a bit of my experience this semester, taking my first step into this idea of being an instructor, teaching MiniJava in compilers. And we'll go into what we have in our next steps. So the concept of what a computer scientist is more diverse. And we're seeing a lot more non-traditional students in the field. That is the white and Asian male. So we're kind of expanding who we are, and we continue to make great strides as we keep going. And computer science is no longer exclusively pursued by those with prior experience. And this is something I really struggled with when I was starting my career. When I came into Marquette University, I felt like I was surrounded by those who had decades of experience beforehand, where that's actually not the case. And about 60% of high schools in the US don't even have any form of computing. Shout out to my high school. But also the field is getting more robust, where we have this idea of set lanes of software developers, data engineers, data scientists, UX design, and beyond. And the demand for computer science professionals in almost every industry continues to grow, where we're seeing more and more industries implement some form of computing, whether that's just data science, data entry, or cybersecurity. And with this, the curriculum design has kind of shifted as we've continued to grow as a field, where the required courses that may have kind of braced every university for the last 5 or 10 years have continually shifted with ABET and ACM accreditations and their requirements, where this idea of a cybersecurity, AI, machine learning, and full stack development courses have really hit the forefront of computing over the last 10 to 20 years as they become more prevalent. And I feel like, much like my grandfather, who still kind of doesn't really trust the internet, this has really happened in front of my eyes, where the idea of OpenAI, and maybe it speaks to my noviceness, but totally took me off guard. So this whole idea of a changing landscape is one that really you guys are probably far more familiar with than I am, but curriculum changes and we have to change with it. And most universities, while they still offer courses in compilers and programming languages, they've gone from this required course that a lot of universities force students to take, or maybe students opt to take, to rather this elective model where programming languages and compilers are now rarely given to undergraduate students unless they seek that out, or they're typically reserved for graduate level students. And those universities that do offer this course offering are often programming languages courses that prioritize theory over actual implementation, where we're working on Blackboard projects or we're working on the ideas of DFAs or Bacchus Nauer form without actually building them in. But for those of us in the audience, and me especially, I want to hamper on the importance of these courses, compilers and programming languages, where they not only teach you how to, we'll say, pivot between languages far easier by not only teaching you concrete syntax, but this idea of abstract syntax and really showing the similarities. But they build on these theoretical foundations that hopefully students have encountered throughout their collegiate experience, where we have this idea of deterministic and finite automata, regular expressions, and language theory that really you interact with at a more granular level in this course than you might at all in any other course. And then there's this whole concept of modular programming, where there's a pipeline and hierarchy management and separations of complex phases. I think for me, maybe one of the most frustrating things that I've had to encounter this semester is getting students to start on a smaller portion of code rather than trying to build out an entire parser all at once. And they come to me after 2 weeks and they're like, oh my God, why would we ever do this? And I'm like, yeah, that's what I tried to get across in week 1. But we're building on what they've learned throughout every other course in their undergraduate experience into this really capstone level project that they get through and they really enjoy. And these interdisciplinary challenges where we're combining not only this idea of theoretical language foundations and modular programming is really what ABET has kind of shifted towards, and where a compilers or programming languages course fits really snugly, where we're able to combine all of these pedagogy or pedagogical aspects into a really engaging course for students. But because there's been this massive shift away from programming languages or compilers, there's really been a switch away in the academic space for those who actually still want to teach this course. So when I was prepping and looking at available course material, I was really interested in finding modern stuff that I could present to students, or just a suite that I could work with. And the available course materials that I was able to find often do a poor job at bridging this generational gap. They're a product of their time, which isn't necessarily bad, but there's significant formatting issues if I even wanted to throw some of the stuff that I was able to find on a PowerPoint. And they're also products of the students of their time, where 10 or 20, 30 years ago, students probably came in with far more experience than they do now. So a lot of the concepts are explained in such a way that worked for 20, 30 years ago. But me coming in, I had no clue what I was looking at. And then there's a dwindling number of maintained projects, where these legacy code bases often are unsupported on modern hardware. So even if you found a project that you were really passionate about, and you're like, wow, students might actually love this, good luck trying to get that to run. And there's inflexibility in the structure of the actual programs that I found, or a lot of the research that's available, where if you want to teach this suite of assignments, you have to teach the entire suite, and there's no ability to kind of swap and drag things around. And there are existing systems that exist, like JFlex, Bison, or Antler, but they're really, they don't really interact well with each other, and there's really a lack of synergy between them. And it's not impossible, but it adds a significant amount of work to an already packed work schedule. And there's also courses that offer, I think Lark is a really famous one in Python, where you can just do like, a single line to read in an entire Bacchus-Naur format and parse an entire grammar. But really, you're not actually understanding, the parsing phase. You're just kind of throwing in a Python library. So for existing systems that we were able to find, we saw that many academic end-to-end compilers exist, right? But they fall into these similar pitfalls that we just discussed, where they often rely on toy languages that really don't teach the interdisciplinary things that we're trying to reach in a compiler's course. So for example, if we want to hit on threads, inheritance, classes, or objects, the vast majority of existing systems don't actually really ever interact with these. So you're really just parsing like a really simple, basic arithmetic language that really doesn't go past 2 or 3 weeks. And the mini languages that we were able to find, the ideas here are to design and incorporate key language paradigms, such as what we just talked about, and we want to connect students with what they know, right? The whole idea of why a MiniJava language is really encouraging is because students have worked with these higher level languages throughout their entire undergraduate experience. So when they get to a compiler's course, they can do at least a language they're familiar with, instead of having to learn Lisp or some other language that really doesn't fit with what they've encountered perhaps in their entire undergraduate career. So surely this is a solved issue, and it is. The second edition of the book that I'm using in class of the Modern Compiler Implementation in Java was published in October 21st, 2002 by Andrew Appel and Jens Palsberg. And it shares a birth date with Blu-ray, which my grandfather also doesn't believe in, Firefox, and Pepsi Blue, which I have never heard of. Anyone in the audience? No. That apparently no one else remembers that either. Oh, we had one person remember Pepsi Blue. But what we wanted to do is we realized that this is it's a fantastic, book and resource, but we wanted to extend it by adding this flexible, modern supporting materials. So implement, modernize, and publicize for other instructors to use. We wanted to extend the existing frameworks to support modularity. So for example, if you only wanted to implement a particular phase in your course, or you wanted to drag and drop assignments, we really wanted to help students get to that. And then freedom for instructors to implement what they want, not teach whatever course you're kind of picked at the beginning of the semester for that one. But we wanted to reduce the barriers for completion, where a lot of the challenges where I was taking the compilers course was getting stuck on where do I go next, and a lack of supporting material. There's not a whole lot of people building out MiniJava programs, except if you're fortunate enough to be at one of the universities that teach this fantastic course. But we wanted to just provide extra resources for students. And then we also saw this as a fantastic opportunity for expansion and educational research, where we could add a lot of these really cool features that we had hoped to have for 5 or 10 years, such as garbage collection, and then build it out on a new instruction set architecture, which really excited us at Marquette University, which is RISC-V. But before we could even consider building a compiler, we had to have a platform that could actually run this code. And there were really 2 paths we could go with this. We could do virtualization, which would have been far easier, but it lacks a wow factor for students, where a lot of the educational research out there shows that if you have students engaged, working on physical hardware, they're far more excited, it builds their self-efficacy, and it's just kind of provides more foundational learning outcomes for it. Which builds us to this physical thing, where educational research continues to highlight the fact that if you have it, you have these higher engagement levels. You have prior research that demonstrates increased learning outcomes, and then you had a higher opinion on how students believe they're doing in their own coursework.
Yeah, so I'm going to talk about RISC-V and the work that we've done at Marquette to port MiniJava over to RISC-V. So those who are unfamiliar with RISC-V, RISC-V is an open standard set architecture. So think of things like ARM, x86, MIPS. RISC-V is one of the newest architectures out there. But instead of taking the approach that ARM or x86 takes, it takes an open approach. So the specifications are freely available online on a public website. There's a whole foundation of various members, big companies such as Google, Microsoft, Samsung. They all collaborate on making this specification open and public for everyone to adopt. And it started off as a research project at the University of California, Berkeley. And it's since grown to, like I said, over 65 members in the foundation, and there's actual hardware being developed for RISC-V. This simplicity and openness makes it a great educational tool compared to other architectures. So when we look at ARM v8 has 1,070 different instructions in 53 different formats, and it takes over 5,000 pages just to document. And you can't just throw that document at a student and expect them to understand it. On the other hand, RISC-V has 6 different instruction formats and only takes 393 pages to document. And most of those pages are due to privileged instructions and stuff, so students don't need to even understand half of that. You can give them just a selection of pages to help them understand the format and the different instructions. The specification, like I said, is very modular as well. Things like floating points are optional. If the hardware doesn't need to implement it and doesn't want to implement it, it doesn't have to. Compared to other things like ARM, where they have various specifications and sub-specifications for the various features. And it's very easy to support 64-bit architectures. 64-bit architectures are kind of the way of the future. And RISC-V, the way they do it is they just add 5 additional pages that says the instructions are increased by this length, or the intermediates are increased by this length, and that's that. So it's very easy to adopt to newer architectures. And it's designed with a future in mind too. They have a little document about supporting 128-bit architectures, which don't exist yet, but headed in the future. So RISC-V, like I said, is still very new, and there's not a lot of support out there for it. Only recently, as within the past few months, have Linux operating systems begun to support it. Ubuntu 24.04, the latest LTS version, supports it on a few different platforms. So there's not a lot of examples to draw from. The hardware is still very much work in progress. and specifications are still being written and updated. The only educational operating system out there is XV6, which is based out of the University of Madison. And on the bottom here is just a little changelog from Ubuntu showing their support for the operating system. So now we're going to talk about porting embedded Xenu to RISC-V. For those unfamiliar with embedded Xenu, it's based off Xenu, which started at Purdue University by Douglas Comer. The past 2 decades at Marquette, we've been adopting it to run on smaller platforms such as Raspberry Pi, RISC-V, as well as the Linksys routers. And we've adopted it for RISC-V because we saw the pedagogical value of using such a simple architecture. So some things that we had to update for RISC-V were memory protection. So each process only has a certain amount of memory that it can use, and it can't overwrite memory for other processes. We weren't able to do this on other platforms just because of the complexity, like I said, with something like ARM. They have a bunch of different page table registers that need to be updated, so it's very complex for students to understand and to implement. We had to implement several subsystems to do this, such as multitasking, semaphores, and inter-process communication, just to get it to run on RISC-V. And you can kind of see here in the bottom here, the approach that we've taken. So previous embedded Xenu kernels have used kind of like the monolithic kernel approach, where everything is just one big, process running in at the same kernel mode. But now we've taken it and we've kind of separated it into a bunch of smaller processes that will run in userland, and they'll do an interrupt to the kernel to go into the kernel and then do whatever the kernel needs to do, and it returns the result back to the user process. And we've documented this more in a separate paper where we talked about using embedded Xenu to teach RISC-V. So now I'm going to talk about RISC-V and MiniJava and how we've actually got MiniJava to compile down in RISC-V and run on embedded Xenu for students to try in their actual operating system. So we previously ported MiniJava to things like ARM, but we wanted to port it over to RISC-V. So the MiniJava, the approach that it takes is very platform independent. So the first few steps, such as the scanner, parser, and semantic analysis, don't require any specific platform, but we really needed to update the instruction selection and the register allocation to support RISC-V. Things like the tree objects, when we're talking about instruction selection, it employs the various visitor methods, and we had to adopt it so that we could use it on the RISC-V platform, changing the various new instructions that RISC-V supports from the ARM ones that we had. RISC-V is a lot simpler. Like I talked about, one example here that we specifically highlight is ARM's 16-bit immediate values for some operations can consist of a 12-bit immediate value plus 4 bits of rotation, which makes it very complex to actually get students to understand, because it's not just a standard 16-bit intermediate, but it can be 12 bits plus a rotation value. So luckily RISC-V makes this a lot simpler, where it's just a standard immediate value. And we go into a bunch of different examples in the paper of how RISC-V made it a lot easier to actually implement this, import the instruction selection from MiniJava over to the RISC-V platform. And this is really cool for students because in the second year, about their second semester, they actually write the embedded Xenu platform. And students go on in their 3rd or 4th year to actually write compilers using MiniJava. So they're really familiar with embedded Xenu, and the students really like working with embedded Xenu, getting it to actually compile, and then getting their MiniJava program to compile and run it on embedded Xenu on actual hardware. It's a really cool thing as a student that when I took the course that I really liked and really enjoyed.
So we have this fantastic quote from Douglas Comer, but I think we're kind of edging on time here, so I'll kind of skip through this and let you guys read this on your own time. In garbage collection for education, we kind of figured that this might be a more solved issue, but when we looked into it, and as I wanted to implement this in my course over this semester, we pretty much found almost nothing. And in 2011, there was a research paper that found 5 courses in the US that teach really any sort of garbage collection and memory management to students, where some courses that do teach garbage collection teach it without implementing and really just kind of use Blackboard theory or really simple linked list constructs, basically fake memory collection. We were unable to find another educational garbage collector that effectively conveys memory management on physical hardware. And this is perhaps unsurprising, right? Because you need control of the operating system to actually go in and clean this memory. But we really wanted to teach garbage collection because it hits on all of these key pedagogical aspects where we can basically have students understand the differences between manual and automatic garbage collection and how that's interacting with memory, the different ideas and different types of algorithms that you can use, such as mark and sweep and mark and compact, and then the performance considerations and how this is affecting your code, and as programs get larger, how that affects performance. The way we decided to implement this was using a mark and sweep because of its simplicity, where we can get this across to students and then allow them to expand on it with building their own optimizations into it, or trying to see, hey, as I run a larger program, how is this affecting the collection, or how does my garbage collector affect my performance on my computer? And over this, the course of this semester, as we kind of get to the close here, I'm currently walking students through this idea of a MiniJava platform. And I know the video isn't running in the background as I hoped this GIF would, but a large push for what I've tried to do and what I've tried to implement this semester is basically modern materials, where before, if you really wanted support on how your compiler was doing, you had to manually write these test cases and go and assess them, or depending on what phase you are at, you can run specific test cases designed for that. But I kind of came to the understanding that some groups are probably going to get further into the compiling process than others, so I really wanted to build out this whole idea of a dynamic assessment system, which determines what phase the student is on dynamically and assesses them where they're at, not where they should be. We also, pushed very hard for modern lecture materials, where we're designing kind of this whole suite of new slide decks that we hope to distribute very soon. My students already have it. You guys might have to wait a little bit. And then custom playbacks, which is an educational tool out of Wisconsin, where each assignment is basically a code along with me, where it throws up a VS Terminal instance. Students get to watch me program the entire demo code that I'm giving to them. And along the way, as they're watching this program scaffold, I can prompt them with multiple choice questions, inline videos, or inline explanations of what specific code snippets are doing. So for future work, we really want to continue pushing this to support RISC-V and the modern ISAs. Our whole goal there was for simplicity. The real hope here is by the end of the semester, we get to this idea of a modular system where we can kind of drag and drop specific assignments depending on the instructor, and optimization. And our whole goal here is obviously to measure the effect, right? Does building a compiler on RISC-V, we think it's simpler, do students? Hopefully we find out by the end of this semester. And yeah, I think that's it. So thank you.
I think this whole RISC-V push is really cool. I also like RISC-V, but the whole idea that you can run on Sino underneath, that is amazing. And I do remember this quote from Doug Comer back in the day. He has more quotes than one about Sino. Yeah, that's just super cool. I'm sure this is going to be good for the students. I'm definitely interested to follow your publications of your material there.
Thank you.
So how many students follow this course, and do you see any increase in the number of students as you have?
Between semesters?
Yeah.
So at Marquette University, I think the course is hosted once every 2 years. I think last time around we had on the number of like 10 to 12. I think this semester we're looking at like 17 to 18. So it's the largest, I guess, compilers course in the last 20 years, maybe.
Okay. Thanks.
Expected something very similar from your group. Awesome. I had done something similar. So we do teach MiniJava. I wanted to share one bit of experience here. We found that there are other schools where the students do not have time to implement full of MiniJava. And we wanted a system wherein the instructors can say, hey, implement not the full of MiniJava, but maybe this visitor, this part, this part. So we created a system where the instructors can say, hey, let the students implement A, B, C, D. So it will create an assignment with those holes. and the students can still get a flavor of the full part, because when all are connected, you see students get a kick out of it. They wrote a full compiler, but they don't have time or they don't have whatever. So we found it very useful if we can provide them kind of some boxes where they can fill in, instead of having to necessarily do all the assignments, because the instructors may have different constraints.
I
Right.
cannot wait to talk to you after
Sure.
after this.
Sure.
Thank you. Yeah, please.
Any other questions?
All right, thank you.
Let's thank the speaker again. So we're a little bit ahead of schedule, so if anybody has any anecdotes about Jens that don't have to be embarrassing, you're welcome to speak up. I think we have maybe one.
Okay, I haven't used a mic in a long time, so see how this goes. So I recognize some of the faces here. I haven't see the ones last time. It's been a while, but to give you some background, I was an undergraduate and I worked with Jens, and not only was Jens an awesome mentor and great teacher, but he just is an all-around really good guy. And I think that as an undergraduate, I really, really struggled with, I was great at computer science. I really enjoyed that. But on my getting through school and getting through my foreign language requirement was definitely really a challenge. And Jens really helped me out in a way that I would not, I can't really ever repay him. And so I'm just here to do the one thing I can do, which is thank you very much, and I very much appreciate everything you've done. And yeah, Jens, I think, did something for me that that he went out of his way for, and there's no way I can repay him. So this is the only thing I could do. So definitely, I'm enjoying JENSFEST. So thanks.
Anyone else? There is a coffee break at 10:30. There's a few minutes until then, so if there's no more anecdotes, you can talk amongst yourselves. The next session will start at 11.
Hello? Hello? Okay, why there's no sound coming out of this? Hello? Okay, somehow this is not working. But this is getting input from... It is working, right? It is just not that outputting that much of stuff. Oh yeah, of course, because... Of course. Yes, of course. So I want to do this. Hello? Reset. Hello? Hello? Up. Too much. Reset, 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 reset. That's good enough. Hello? Okay. Why this is not outputting sound? Because I muted. Hello, 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 hello. Okay, now can you please go to stage 16.9? I just want to see, like, the only reason I did this is for the stream people to hear clearly. You don't need to do that. Just do talk transition. Thank you. Here? Talk transition. Talk transition. Okay. Thank you. We have 10 minutes, so JENSFEST. Testing. Testing. Oh yeah.
Oh yeah, is the stream a bit slow?
Yeah, there is a lag.
Should I turn this off? You want me to say something now? Yeah, okay. I'll do, is that okay? Right.
Oh, it's underneath the, yeah.
Sorry,
It's a cheat sheet for them.
Okay.
Based on this first paper? Is it based on, oh, the denotate Jens had the famous denotation system. Okay.
Yeah, it's great. Thank you.
Thank you.
The visor moved to Tufts. He was like,
Sorry, can we turn this off in the meantime until I start?
1 minute. Okay, let's have a seat. We're going to get started. Could everyone take your seats, please? We're going to get started. Okay, great. Welcome back. This session we're going to hear from Jens's ancestors and descendants. We've got first up Peter Mosses, who was Jens's PhD dissertation advisor, talking about verification of denotational semantics of inheritance. You defined it, but you didn't verify it, right? So now, 20 some years, 30 years later, we got to verify it.
Thank you for the introduction. First of all, congratulations, of course, to Jens in this celebration of in connection with his 60th birthday. I gather it's not quite his 60th birthday yet, but still we'll celebrate as if it was. I'm delighted to be able to contribute to the celebration today. To start with, I'd like to look back 35 years to when Jens and I were both at Aarhus. He was the first PhD student I ever supervised, and a really good start to my career as a PhD student. But supervision is not really the right word when it comes to Jens. He had no need at all for my supervision. I gave him some advice from time to time. As you see from this publication list, this is just taken from DBLP, that he didn't exactly restrict himself to his thesis topic. He started a very fruitful collaboration with Michael Schwarzbach on type inference, and those highlighted ones there are the ones that are co-authored with Michael. Unfortunately, Michael is no longer with us. With Dexter Cozen, also, he co-authored the first of his many Popple papers. It wasn't published during his PhD studies, but I'm sure it was written during his PhD studies. What I'd like to do is to look at the very first of his papers, which is this Uppsala 1989 paper. How many people were at Uppsala 89? Okay. Oh yeah, that's good. That's not. You may remember that it's co-authored with William Cook. Again, sadly, no longer with us. Died a few years ago. It was written when Jens was in the first year of his PhD, and so the Uppsala was in the autumn of his start of his second year. It's also one of his most highly cited. I think it's his second most highly cited paper, with more than 500 citations on Google Scholar, which is far more than I ever had in any of my publications. When I first heard about this celebration, and somebody alerted to me the fact that Jens had got older since he was a PhD student, of course I started looking around for an idea for a paper, well, I started at the beginning of his DBLP list, and of course this was the first paper that I looked at, and so the idea that I had, well, first of all, when I reread the paper after so many years, I was impressed by how elegant the semantic definitions were. Simple and elegant, and the proof of the equivalence between actually an operational and a denotational semantics using step index was also very elegant, and not unrelated to my own interests as well. So my initial aim with this, what is now turned into a paper in the proceedings, which you can download because it's open access, was that I would simply type in Jens's semantic definitions into a proof assistant and verify it. And I'd also wanted to experiment with an alternative form of step indexing. I won't go into the technical details of that, but I wanted to use a proof assistant because nowadays that's more or less mandatory in connection with any publication, that you don't just put an ordinary LaTeX proof in, but you put in something that's machine checked. And for various reasons, I decided to use the proof assistant Agda. How many people have used Agda in the room? Right. No, there's actually slightly more than I expected. It's a relatively new proof assistant. It's not as old as Coq. It's related to Coq. But in any case, if you want to read Agda, you can read the paper. In this talk, I'm not going to be dragging you through the literate Agda specification that takes up sections 4 and 5 of the paper. In the rest of this talk, I'll first talk about denotational semantics and fixed points, because Jens's original paper and analysis of inheritance with William Cook was based on the notion of fixed point. This also very closely related to my own start in denotational semantics. We'll look at the semantics of inheritance, which Jens gave both an operational method lookup semantics and a denotational semantics. I'll give you a little taste of how it looks in Agda. And then we'll finally look at how you prove a lemma in Agda. So let me now go back even further than to Jens's paper, go back to the work of my own supervisor, Christopher Strachey. And he wrote a paper in the proceedings of an IFIT working conference with a delightful title, Formal Language Description Languages. You can parse that any way you want. It was published in '66, but the work was done starting in '63, and it was written in '64. So that's really quite a long time ago, something like, 60 years ago? I don't know whether you'll be able to read this at the back. Can you read that at the back? Yeah, okay. So then I won't try to read it out verbatim just to save time, but just let me say that Peter Landin, I guess many people in functional programming know Peter Landin for his contributions to functional programming. He was translating Algol 60 into lambda notation, but he had an abstract machine and he had side effects in his lambda notation and a jump operator. So it wasn't a pure lambda notation. Strachey very much wanted to not have any machine in the picture, however abstract. He just wanted to have pure lambda notation because he wanted essentially to be defining pure mathematical functions. He'd become convinced that lambda notation and pure functions was the way to define the semantics of programming languages. He was, as I say, wanting to define semantics by translation to lambda notation with the intention that those lambda expressions, they would be simply defining mathematical functions. But he had a problem. He needed to use a fixed point operator. And that fixed point operator had a self-application in it, very similar to the self-reference that you get in object-oriented languages. There was no known interpretation as a function of that fixed point operator at the time that Strachey was doing it. So he was doing all this, he was wanting everything to be a pure mathematical function, but here he had an operator which actually was not. And it has the unfolding property that if you apply it to a function and do some reduction, then you get this expression here, which is where f has just been wrapped around it, and you can carry on doing that, and it unfolds. This is a fixed point. It is a value, an argument to y, such that it's an argument to f. This y of f expression, such that when you apply f to y of f, then you get y of f back. So that's a fixed point, and that was a well-known operator. Strachey was using it. Dana Scott was horrified at that because there was no known mathematical interpretation. And so he comes along with his domain theory. which was actually, first of all, he tried to prove that there could be no model, but then in the process of the proving, he actually discovered how to construct the model. This is called the D-infinity model, and it's quite a famous model of the lambda calculus based on the notion of continuous functions. And then you have a fixed point function, this fix here, for any domain D. If you apply it to a continuous function from D to D, then it gives you the least fixed point of that continuous function. It can be defined in the same way that as a so-called Kleene approximation limit. And then Scott and Strachey together, that was essentially denotational semantics in the early 70s. And I was fortunate enough to be in Oxford at the time as a student of Strachey and also to have access to Dana Scott, and it was a very formative part of my development. So now back to Jens. So we've got fixed points sorted, and Jens, I don't recall exactly how much Jens was working with denotational semantics. He was working actually with action semantics quite a lot, which was a hybrid of denotational and operational semantics. But it seems he really liked this denotational semantics. I'm going to show you some snippets from his paper. So hold your hats. He abstracted, together with William Cook, they abstracted from the concepts of object-oriented languages to method systems, which was a very simple thing that still had inheritance in it, but didn't have any of all the nasty features like imperative variables and lots of other things. So they had this part with the syntax of the message systems with these very, very simple expressions. This one here is calling a method M in what they call an instance, or you think of it as an object given by the value of E1 and passing it the argument E2. Jens, I guess you remember this quite well. Maybe everybody else is going to have to take it on trust. Note also there were some extra operations with a class hierarchy that was assumed to be finite and where the root had no methods. Note in particular this parent operation here that takes a class and tries to give you the parent, but of course if it's the root already, then there is no parent, and so think of this question mark here as a kind of maybe type that it might or might not give you a class. And here you see that it's used to give a case analysis between two different expressions. The square bracket notation is case analysis. So this will be significant in a moment. There are also some semantic domains around. One of the nice things about denotational semantics is you can just define your domains recursively without any regard to positivity or contravariance. And in particular, these domains are nastily recursive in that this domain of fun includes functions from values to values, and those values could be behaviors, and behaviors could essentially include functions again. So there is a real cycle in the definitions of these, but that's fine in denotational semantics. We know from the work of Scott and Strachey, or rather Scott I should say, that such domain equations, they have least solutions up to isomorphism. And you don't even bother to mention the isomorphisms. So now let's look at this is the method lookup semantics with three mutually recursive functions, send, lookup, and do. I'm not going to take you through all the details, we don't have time for that. But at this point I really have to, in a rather embarrassing way, quote the acknowledgement at the end of this paper from '89. The authors would like to thank me for helpful comments on the second part of the paper. That should imply that this was entirely accurate and bug-free, this semantics, right? Now, this is the embarrassing bit. So remember that parent is something that might give a class back, so it's a maybe type as a result. Here it's used as an argument to lookup, which takes a class, not a maybe class. Now you could say that, well, okay, in this case it's guarded by root. It tests whether it's root, and so here it's in a sense safe from a dynamic point of view. But here there's no guard. Okay, so this was not something that I noticed when I reread this semantic definition. It's not something that I ever noticed when I originally read it, but it is something that Agda noticed when I fed it into a proof assistant. And that's not the only thing here. Remember that an expression can evaluate to a behavior or a number. Now, I'm not really quite sure what Jens expected to happen when you called a number with a method and an argument. This M is a method name, essentially, and this is the argument. But if this is not a behavior, it's not expecting to be sent a message. Again, that was something that Agda did. The third thing is actually very trivial, this double use of F here, which Agda also complained about, but was actually fixed in the journal version of this paper. The other two were not fixed in the journal version of the paper. So the referees of the paper, the reviewers, also had the same blind spots that I had. So a bit embarrassing for me personally. By the way, I should say that I didn't go out expecting to find any bugs in Jens's semantics. I was wanting to just verify that they were perfect. Now this is the denotational semantics, and because Jens had proved it equivalent, then indeed you expected to have exactly the same issues. So to be really disconcerting if it didn't. Now I'm going to give you a brief taste of what it looks like in Agda. So just to recap very quickly, Agda is a purely functional programming language with dependent types. If you don't know dependent types, then read the paper a bit and hopefully you get the idea. It's also a proof assistant based on the Curry-Howard correspondence, which says that essentially a proof is a program, and the formula it proves is the type of the program. Again, please just accept that that's a fact of life. So now let's see how it looks with this semantic definition. We're going to introduce a concept of domains. These are all assumptions of this module that you can write in Agda. Agda doesn't really care whether you can discharge these assumptions. And in fact, the idea that you could take a fixed point of any arbitrary function here from the carrier set this is a carrier of the domain, the set of elements of the domain, that you could take an arbitrary function here and find its least fixed point is just an unrealistic assumption, but that doesn't stop you using Agda to check the definitions. So here's some more Agda. This is just the way that we're going to deal with classes without this parent operator around. We're using a data type here, an algebraic data type with essentially having an origin class and subclasses of that. So you automatically get a finite hierarchy. When we define domains, then we're going to use isomorphisms here, and that introduces implicitly in Agda with these funny curly brackets, introduces overloaded functions to and from between the left and right hand sides of a domain definition. And finally, you have the syntax of the language more or less as in the paper, just a bit simplified here to fit in the paper properly. So here's the definition in Agda of what you'd seen previously in the denotational semantics copied from Jens's paper. It looks a little bit messy with all these froms and tos, which are the isomorphisms, which you never bother to mention normally in denotational semantics. So let's get rid of those. And it looks a bit, if you squint now, then it really looks pretty much like Jens's original definition, except for this case, which is now much more complex. Remember that it's possible that this first expression could be evaluated to a number, so we're going to cover that case explicitly, and also it might not implement that method, so we also want to deal with that case as well. Okay, so now towards verification. Just very briefly, the idea was to have an approximate semantics based on the notion of fuel, an extra argument, a natural number that you fed as an extra argument, and then you just counted down. The only place it counts down is actually from here, I think, with self from n to n minus 1. Everywhere else it's just copied over. And this is for n greater than 0 that you have these equations. Then there's a lemma that I'll illustrate how one case looks in AGDA. This is the whole proof in the paper of that lemma, just by structural induction on the syntax. This is how the statement of the lemma looks in AGDA. And again, there's this issue with the parent occurring there. Yep. By using this child here, which essentially says that here we're dealing with a class that has a superclass, then we avoid that difficulty there. Then the actual the particular case for self, this is the way it looks in AGDA, and again, you can relate it very closely to the way it looked in the original. I'm running out of time, so I'm going to conclude now. So you can find many more details in the paper and in the other material. But before I get to the real conclusion, I'd like to give a little birthday present to Jens. So this is the book in which Christopher Strachey's paper appeared. This actually is not just any old copy of this book. This is Christopher Strachey's own copy of the book, which I inherited when he died in 1975. So even if you already have the book, then you don't obviously have that particular copy. As I say, this is not available online, and so now, Jens, you have something I hope you will take good care of and pass on to your own descendants. So let me conclude really now what I've done, and it drew attention to some issues with the difficulty of taking a denotational semantics and pushing it into AGDA and verifying it. Not due to it was good that it found a few inconsistencies, but actually it was quite painful to get to that stage. And what I'd like to do in the future, if I get the chance, is to make it easier in AGDA to just put in a denotational semantics without all that extra fuss with making these isomorphisms explicit and things like that. So thank you for your attention.
Thank you. We do have time for 1 or 2 questions. John, you can come up and get started. I do want to say also that if anyone else can find bugs in 35-plus-year-old papers of Jens's, that would be a great thing for the rest of the... but if you do, you also have to give him a really nice gift. So
many thanks for this book. This is like precious. So this is my academic grandfather, and a very famous one at that. I want to say one more thing. This proof that Peter talks about, actually the idea came from him in a way. I went to him and I said, we're trying to prove this, what do we do? And he pointed to a paper by Peter and Gordon Plotkin on limiting completeness, which is a difficult proof about something also with denotational semantics and so on. And I read that, and I think I got the idea. And what I learned today is that in a way that was very early step indexing. But so in many ways, maybe that paper was the very beginning of step indexing, which is now used everywhere.
The one that was published and got all the 500 citations, my paper with Plotkin has about 7.
But anyway, I think many lesser men would have said, look, I'm your PhD advisor, I gave you the idea for how to get to the proof. He would have said, I want to be a co-author. And he never did that. So this is like the most generous person I've ever met. He never asked to be a co-author of anything I was working on. And he just helped me and advised me, and it was wonderful.
Great. You have a present for Jens?
I don't. That's a tough act to follow, to be honest.
Great. Well, next up is John Bender. John was one of Jens's PhD students. Graduated, what, five years ago? Okay. And doing lots of cool and difficult stuff with proving things about concurrent compilers. Yeah. Okay. John.
Well, thank you. So first thing I'll say is if you find all of this sort of laborious and overly detailed and exhausting, take your complaints to Jens. None of this would have been possible if he hadn't been kind and invited me into his program for a PhD. Do I need to just unplug it and replug it maybe? Yeah, that's not sure. This is the best game possible. I'm right in the middle of my jokes. All right, success. More importantly, though, when I started my PhD, I didn't even know how to do a proof. So I remember picking up I remember picking up the book, How to Prove It, literally, just to make progress here. And do you want to futz with it? Yeah. Okay. This is going to be a short song and dance. Anyway, over the course of my PhD, we went from doing analysis with regards to memory models. Let's hope it stays that way. And I think at one point I was like, hey, Jens, I'd like to do something more theoretical. My presentation is going to remain theoretical here as well. And I remember very distinctly Jens being completely open to that. Like, again, I had no background in it at all, but he was totally open to me trying. We did a lot of great work. We ended up with a very nice paper about Java's memory model of all things, which is, there's a lot of theory in that paper that's almost the entire thing. So, and a lot of nice lemmas and theorems. And I do most of my work today now in Coq. Okay, we're going to hope that works out. Okay, great. Wonderful. Okay, so anyway, all that is to say, let's talk about ComCert in the context of concurrency. My goal here is really, I'm just going to introduce the problem. This is a presentation that probably needs like a full day to honestly get through all the details. So we'll just start with the problem and see where we get. Okay, so just to start, everybody, I think people are familiar with ComCert, but in general, there's this nice paper about a tool called CSmith that found a bunch of bugs in compilers, right? Okay, so we know that bugs exist, and a nice thing to have, in certain contexts is a compiler that guarantees with some reasonable assurance, for certain properties that those things will carry down, that you won't have bugs with respect to, maybe reasoning you've done about your code. ComCert took a lot of work. Compilers, even relatively simple compilers or complex pieces of software, so much more the effort to do the proof along with that, right? So there's a big picture here. This is just sort of supposed to evince the fact that it's a complicated project. But most of the work is in the proofs. Okay, so that'll be important later. Famously, it only works for single-threaded programs. So if you have threads, sorry, you're out in the cold. And vaguely, threads and concurrency are important. I see nodding heads, so that's good news. I don't have to fight about this point. Okay, great. So let's talk a little bit about this. So I'm not the first person to attempt to address this problem. Like our group is not the first set of people to address this problem. So like, what are they doing in prior work? Okay, so Andrew Appel and his group had done some work on this. The kind of core assumption there was that in the memory model, all your programs would be well synchronized, right? So if you are familiar with program analysis or doing any kind of concurrent programming, making sure that your locks all work together well, that's quite difficult. Separately, there was this work from the folks at MPI. I'm a big MPI stan. I like Derek Dreyer's group. They do good stuff. But they attempted to kind of do this, but and I'll talk about the way the caveats for their work. But they ended up kind of having to shred large parts of the compiler for the proofs. Like the proofs weren't going to work in the context of how they designed the semantics, right? So that won't work for us. I don't want to rewrite large parts of the proofs of ComCert. At most, I want to have things that are adjacent to the existing proofs. So that kind of falls outside our sort of desiderata. Okay, so yeah, our goal is we want to take the proofs that exist in ComCert that are about single-threaded programs. We want to take that reasoning and we want to lift it up to multi-threaded programs. And I want to do that in a way where I don't shred the existing proofs, because those are exhausting and laborious to put together. and so as a consequence, we can also pull in upstream updates, right? So if people are working on ComCert, they're doing things constantly, making it more interesting, improving it. If I shred the proofs, it's going to be really painful to bring in updates from upstream. Okay, so there's software concerns, but it makes the problem, slightly more interesting. Okay, great. So let's talk about what it means for a compiler to be correct in the first place. I am not going to assume a whole lot of knowledge about this. Even people in programming languages have like a vague intuition for what this means, but we'll make it a little bit more concrete. Okay, so vaguely, the big black arrow is a compiler. We're going from C to some instruction set architecture. Okay, and vaguely the goal is all the reasoning that I did about my C program should carry forward to the output in my ISA. And reasoning could be broadly construed here. The details of which properties apply, what types of properties apply is subtle. And we could talk about that offline if we want. So from invariance to safety properties to even liveness properties in certain circumstances, which you can get with the simulation in ComCert. Okay, but the basic way this works is, if you have some state in your instruction set architecture at that level, and it makes some it makes some step or does some work and produces some observation O, then supposing you have some equivalent state in C, roughly speaking, equivalent state in C, related by some simulation relation, then you have to show, the gold part is you have to show that you can take a step with the same observation, so those O's have to be identical. Keep that in mind for later. And then those final states are equivalent, right? Okay, so if you've ever encountered simulation, this is like roughly the thing you would expect. The idea here is that if we start with the assumption about the instruction set architecture step, and then we're going backwards, that's the backward simulation, which produces a subset sort of roughly of behaviors, right? So, and with that subset of behaviors, then our properties that we proved about C will carry down to the behaviors of the instruction set architecture. Okay, so this is what compiler correctness, roughly is broadly construed. Okay, so that's the background. Okay, so in ComCert in particular, they have a requirement, which is that all of the target semantics for the compiler passes have to be deterministic. And the reason they have this is because they don't do a backward simulation proof. They don't start that way. They do a forward simulation proof and then derive a backward simulation from that. And the reason that is because going forward is easier. When you do induction in the forward direction, you're doing it over just a program. Whereas if you do it in the backward direction, you're doing it over something optimized, right? So you have that extra painful step to deal with. So what they do is, and again, there's this, total aside here, this is like fun historical fact, but like a reasonable question is, well, could we do one with a backward simulation and avoid that? And the answer is surely, but this is the one we have. And up to the point that people had, ComCert existed, people wondered if a project of this complexity doing verification was possible at all. So anyway, that's an open question. Feel free to try it for yourself. Okay, so it's required to be deterministic because of the way they derive a backward simulation from the forward simulation. Okay, we can talk about, if you want to hear the details of that, I'm happy to talk about it after the presentation. But for now, just know that determinism is important. And obviously, maybe you see where this is going. Concurrency is not particularly deterministic. So, okay, so we're going to keep that kind of fact up in the top right there for reference. But okay, so let's see, what does it look like when we have a concurrent program? And why is this a problem? Okay, so again, this slide's maybe not really for you guys. This is a little bit more introductory. But anyway, if you have two writes to a particular variable and then you have a read to it, there's obviously non-determinism even in the single thread semantics on the left, right? Because there could be two values that X could evaluate to in that second statement, right? So that's no good. That's not deterministic. That fails our kind of criterion there for semantics. Okay, so this is the crux of the problem effectively with ComCert and concurrency, is that this requirement of the way the proof structure is set up is that there's determinism. Okay, great. All right, so someone out there will be thinking, but wait, in single-threaded programs, there are sources of something like non-determinism already, right? What if we're calling rand? We have some external source of non-determinism, right? Okay, great. This in principle, depending on how you define your semantics, this could evaluate to any number of states up to rand max, right? Okay, so how is this dealt with in ComCert now, even for single-threaded programs? Well, the key is to note that you can externalize the non-determinism, right? It's a system call. So as long as you kind of basically roughly quantify over all that, kind of symbolize the value, then you can get back a single step, right? So system calls are a special case. If you're familiar with, reasoning about non-determinism in programming languages, externalizing the non-determinism is like a trick you use to, work with equivalence, right? So this is an old trick. It's a good trick. And so as a consequence, it's a fairly natural trick to try and apply to this Anyway, so yeah, so you recover determinism in this case. Okay, so the key conceit of the paper from the MPI folks was, well, why don't we just do that trick again? What if here we just, so recall that this is non-deterministic. What if we just did the same trick here, where we said, okay, now reads and writes to memory are observable behaviors. We're going to externalize the non-determinism of what happens when I go off and look at memory, and maybe, you know, I'm fighting between two threads that could have written to the same variable. So we'll just externalize it, and then you get this back. So that's what that paper does effectively. The problem here is that I cut out the slides for describing the problem. Okay, so now I'm going to wave my hands furiously. Okay, so now it's part of the observable behaviors of the program, right? And you'll require, you'll notice it says T up in the top right, which is another mistake. Wonderful. The T there, which was the O in the original slide, has to be identical between the source and the target. Those have to be the same, and intuitively that's natural, right? When I compile a program, if it has some observable behavior to the outside world, it would be very bad if I was changing that, right? That's like the key way in which COMSORT preserves correctness for programs. Whatever the world would observe of the program is preserved as the compiler does its operations. Okay, so that's the T, you know, previously the O being the same thing there. Okay. Here, what I've said is all my memory operations are suddenly observable behaviors, which means that in the C program, any memory operation now has to appear as an observable behavior in my target program for the ISA, right? Well, that's a comically bad idea for, you know, a compiler, right? Because one of the things that compilers do quite a lot is move around memory operations, remove them depending on the context, right? So suddenly you're left in, you know, with lots of compiler passes which just don't fit into the general architecture of the proofs, right? Okay, so this clever trick doesn't work in this case. All right, so let's see what we did, because, you know, key insights, whatever. Okay, so the first thing we realized is, well, you can't externalize it according to the steps in the semantics with this like notion of observable behavior, but you can advantageously guess a lot of non-determinism and then just stuff it into the single thread. And then if you make all the, basically if all the non-deterministic choices the thread would have made about reads and writes and these pairings, or, you know, interleaving is part of a guess, you can give that to a thread, and then it doesn't need to make any non-deterministic choices, right? It suddenly has all the non-determinism, and everything after that is deterministic, right? So first thing we're going to do is we're going to create a prophecy of all the non-deterministic choices. Okay, so that's the first thing here. So what does that look like? Okay, so how am I doing on time also? All right, I might even be able to get through part of how we solve this problem. This is incredible. All right, so a standard concurrency semantics looks something like this. And Jens at this point will be very happy to see that the validity predicate that you would expect from a memory model is like left off to, you know, as an exercise for the reader after my PhD. So okay, so you have a list of threads, you have some memory representation, and then at the top here you're going to have the thread is going to do some operation. It's going to tell you, okay, I did a read, and I'm pairing with this write on the other thread, or, you know, I got the value 2 as opposed to the value 3 or value 1. And then you're going to have the memory model say, yeah, that event is acceptable, right? That's an okay pair, you know, it's an okay pairing of a read and a write. That fits within the constraints of our axioms for the memory model. And then that allowed you to take a step in the concurrent semantics. Okay, but the key problem here is, again, non-determinism, right? So the thread is doing some non-deterministic behavior. So anyway, what we're doing is we're just, this took a while to figure out, but is really kind of like trivially simple in retrospect. What we're doing here is we're just inverting the relationship. We're going to do the guessing outside the thread. Okay, and this has lots of subtle implications later that we won't even get to, but we're just not letting the thread do the guessing. We're going to do the guessing at the concurrent level and tell the thread what it's allowed to do. Okay, and the good part about that is that now the thread gets to be deterministic, right? And so the key thing, remember, is that COMSORT is all its semantics are single-threaded, and now its determinism is, you know, recovered effectively. So we get to hopefully keep those proofs with a minor modification, which is this parameter of the memory state that it needs to do its operations. Okay, great. These are the rest of the key insights. The one we'll get here is the second one, I think, and then the third, fourth, and fifth we probably won't get to. Okay, anyway, I think I put this list here because there's a lot of stuff you have to wade through after you make this kind of like first insight, right? It's like one kind of cascading minor issue after another you have to kind of sort of solve all the way out to the end, which we effectively have done. I'm happy to talk about later offline if y'all want. Okay, so let's talk about this. So what we've said here is that we're going to come up with, we're going to guess some memory, right, at the multi-threaded level. But what we're really saying is also we're going to have like some memory state we're going to pair with the program. And there's going to be some quantifier here, you know, roughly that says something like, if the target has some memory at which it's able to do a step, then the source, there exists some memory, and some related memory at the source that allows it to also take a step. So the key thing is we've introduced this existential up here, which that would constitute a large modification to the existing proofs, right? Again, that's our goal here, is to do as little surgery there as possible. So that's bad. Okay, old trick, we scolamize. We just basically, we ask the people who are doing the pass to give us on the side a definition of how we should be mapping memory back. So suppose you made a pass and it was reordering writes and reads. Now your memory mapping going backwards has to basically reverse that process. Okay. But keep in mind, it's got to be a general thing. So we're going to run into that here as a problem. So, okay. So the rest of this is, how am I doing? I think I'm doing okay. How much time do I have?
You've got 5 more minutes if you want 5 minutes. 5 more minutes of talking and 5 minutes of questions.
Okay, so that depends on how confident I am in answering questions. All right, let's see. I'm totally confident answering questions. I'll just ramble here for a few more minutes and then we'll stop, and that'll be how it goes. Okay, so we have some other properties here. So the first thing is that, okay, so now we have this mapping. We've solved this sort of existential problem with another old trick, which is to scolamize. But this, at the end, when we do this final proof, where we lift the single-threaded proof of the compiler into a backward simulation for multiple threads, this is going to be effectively the composition of many passes, and thus like many mappings, right, that we've these scolam functions. So we're not going to know anything about f. Or I mean, even if we could know something about f, we could inspect it, I suppose, but then it's going to be very complicated and annoying. So what we want to do is come up with some general principles about this mapping that will allow us to do the lifting proof in a sort of straightforward way. And then as long as all the mappings adhere to these principles, those compose in a nice way along with the mappings themselves, then we can get the proof at the end. So the kind of core one of these is like a notion of monotonicity, which is that if you're doing a mapping, between a target and a source to kind of generate the memory it needs to take a step, you don't want to do weird things effectively, right? You don't want to cut off behaviors. You don't want to foreclose. You don't want to end up with less information effectively for the step in the program to happen. So that's like the core conceit here. And then this is like, this along with the definitions for the prophecy is what allows us to basically get the proof to go through. And then there are some implications about this later where I'm completely leaving out what the preorder is here. So that defining the preorder actually turns out to be maybe the hardest part of this whole problem. So that's like the next thing. Do we want to like suffer through this? Good question. I feel like everyone out there is falling asleep maybe. Okay, so anyway, let me just say this about the preorder very quickly. You can look at the bottom of the slide. A very natural thing to do would just to order memories by extension, right? So bigger memories, you're farther along in the program. Okay, that has a very natural counterexample if you reorder stuff within your memory, right? If your optimization is doing the reordering, if you apply the mapping to unreorder it, it's impossible to find an extension. So these kind of like a sort of naive approach won't work in this case. So anyway, we have to go on to address this. We do this through predicating the preorder, and then we have to come up with a theorem about the composition of these monotonicity predicates and things. Okay, cool. Fairness, all right, this matters. So the details of this I do not have time to get into, but fairness and safety are very important in the proof of the compiler as it exists now. So you have to derive some notion of safety for a single thread from multi-threaded safety to get this to go. This turns out to be thorny and subtle, but interesting also at the same time. And then, so the main thing is what we have left. We need to, we want to alter some of the way the preorder is set up for cleanliness, this safety issue that I was talking about. And then, we want to move on to actually implementing in ComCert. So we've done this with like a toy language with the actual structure of the proof from ComCert, but you can instantiate that with any language you want. So we've done that. And that's it. So this is a thank you for you all, but it's especially a thank you to you, Jens. I really appreciate this. I love my job. I love working on these things. And I simply wouldn't have the opportunity to do this if it weren't for Jens taking a chance on me getting a PhD. So I really appreciate it. Thank you all for listening.
So this is super cool. So you did this for sequential consistency concurrency, I suppose.
So the cool, so at first I was like, let's do x86, and then I got bogged down, and it just turns out that the whole thing is parameterized by the validity predicate. So we just abstract out and say like, please don't. Like that's like another paper you can go read, and there'll be one. In practice, what'll end up happening for the actual compiler is we'll choose probably a release acquire fragment of C++ because then you avoid the thin air read problem. Because then you have no reasoning principles at all. So yeah, that'll be the basic one.
Very nice.
Yeah,
Of
so
course.
we have a story for that at least.
Super cool. Can I ask how big is your group working on it?
It's me, and I have had 2 interns.
Okay.
It's basically me. Yeah, no. That's not true. That's not true. That's not true at all, actually. The 2 interns I've had, Eleanor Tang is at CMU now. She's super excellent, really excellent. And then Anjali Paul is at UW, and she's working with me year-round now. So these people were excellent. To even characterize it as me doing it on myself is silly, honestly.
More progress is going to happen. This is cool.
Let's hope so, yeah.
Yeah, cool work. It's, I guess, very similar to Jens's question. So you said it's parametric on the memory model. Have you thought of how to pass the parameter, not just as an enumerated set to choose one of these from, but maybe a model in, say, herd or something?
So as a default, you would sort of assume that whatever the model is, it'll be one of the axiomatic models you would grab off the shelf. However, it's worth noting that there already exists an intermediate memory model project. I think also from like the line of people from MPI, where they did the work of saying, okay, here's the C memory model, and then they have the like outputs for all the, this sort of like the refinement outputs for all the various architectures. And I expect that we're going to need that at some point anyway, even if we just sort of fix an architecture and move on with our lives. So to your question, yes, we've thought a lot about like the ways that validity predicate will matter in the future for the project. Yeah, that's a great question.
Maybe I'll just ask one question. So one of the motivations, which makes a lot of sense, is that you want to be able to reuse much of the single-threaded reasoning. So can you give a sense of like, let's say there's a constant propagation optimization already in there.
Yep.
Like what in general does it take to then make that safe in a concurrent setting?
Okay, so one of our parts of our research proposal is that we made, like, we hypothesized the amount of code changes required. So one thing we already identified is that you have to add this parameter to semantics everywhere. So that's one thing. Otherwise, the lemmas and everything about the mapping and stuff should exist entirely off to the side. I think there's a big open question I have right now is locality, right? So one thing is if I know the memory is going to be local, I should just be giving the mapping should just be the identity mapping, right? I don't want to deal with that. I don't want to have to do any extra proving in that case. That I have not sorted out, and that is an open question. This is like the key question right now is like, what is the actual impact on doing the compiler? In principle, we've left it almost all to the side. In practice, I still have to figure that out. This is a really great question.
Okay, let's thank John again.
Thank you all. It's the button on the top.
Okay, I think we've got, is this the last talk in the session? The last talk is Ben Titzer. Ben was one of Jens's PhD students 20 plus years ago. So Ben was working for his dissertation on this language called Virgil, and apparently he's still working on it. So I'm not sure how we let him get a degree now that I think about it. It seems like it's not quite done, but we'll hear what the progress has been since 20 plus years ago. So.
Has it not been on the whole time? So basically, it means that you can write something like this. You don't have. This is effectively what you have. You have a ref of L is effectively a pointer to something where you lay out the fields exactly as they're expected by the code that you're interacting with. And you have no choice but to deal with what the kernel asks of you. And it's represented as a pointer to an object plus an offset. And so that means that the garbage collected object can move, but the start of the object does not move. And so you can actually point to both something inside of a byte array and also outside of a byte array in the heap too. So it's kind of designed for being able to memory map things too as well. But this paper is not about that. It's about doing something similar for algebraic data types. So originally, Virgil only had classes and arrays and tuples. Can we turn this mic off? I think there's some, okay. And those are all on the heap. And so we need to point outside the heap, and we need to also do, I mean, obviously, people have done lots of encoding ADTs into classes. It doesn't really work. You really want ADTs in your language. And I finally concluded that the PLDI paper that I referenced said, you don't really need ADTs. You can encode them with classes. That was a lie. You want ADTs in your language. So this is the syntax that Virgil has. It's a lot like any ADT you might define in a functional language, just with more curly braces, because otherwise the C programmers will lose their minds. So we define a few cases here, and they have fields sometimes. You can desugar this into classes, of course, and that's like the first implementation that I had in my compiler. You basically just define a class inside for every one of the cases, and there's a superclass for the top. But that's inefficient because they're all on the heap, right? Every time you make a new value of one of these, it's an allocation. And so obviously functional compilers don't necessarily represent them that way. You can represent them any way that you like, as long as you do the recursive comparison so that there's referential transparency. So some ADTs are actually hotter than others, like super hot, and you have like bazillions of them, and so you don't want to allocate them all on the heap. So this paper is all about some new annotations that are not semantically meaningful. So it doesn't change the program's behavior in any way to add an annotation like unboxed, but it just makes the compiler represent them differently so that they're more efficient. And so you can unbox all the cases by putting that annotation at the declaration of the ADT, or you can unbox a single case, in which case the compiler will make sure to unbox that one case, and all the rest of them it can kind of be boxed. So what does unboxing actually mean? It means that we're not going to allocate an object on the heap and have an indirection to it, but instead we're going to use multiple scalars or multiple words. And so I use the term scalar. It's a super overloaded word in PL literature, but basically think of it as a machine storage unit. You need at least to have one unit for the tags, so you need to be able to distinguish the tags. But what are the units themselves? I, again, stupidly chose, actually me and my student together stupidly chose scalars and to overload that. And it's effectively a register class. So a scalar can always go into a machine register. And so depending on your target, you may have some set of scalars. One target has some set of scalars. Another target has another set of scalars. It's the compiler's job to choose what that set is going to be used to implement the ADT. So it is not a word. It's not the same thing as a word, sorry. Some of them have opaque encoding. So ref is basically, this is a pointer where you do not get to see the representation of it. This is like a typical thing in a safe language. Then the other ones actually all have transparent encoding. So you can actually see the bits in one way or another. There's another way to slice this too, which is can you store a reference in there or not? So ref, obviously you can store a ref in there. R32 and R64, you can store a ref in there, but they're effectively kind of like a tag pointer. And the idea is that we're going to be able to use that to unify with primitive types so that you can pack two things into one word, and the tag will be distinguished by the runtime system. The other ones cannot store references, so you cannot mix them up. So you can do all the bit level tricks that you like with the other ones, and you can't confuse the garbage collector. So once you have source types, like classes and arrays, obviously they're going to map onto references. They can be opaque references. On the JVM, they can only be opaque references because there's no such thing as a tag pointer on the JVM. But on native targets, maybe we can use the other two. And then when you have integer types, they can map onto these B32s, and float types can map onto the F32s or F64s, and maybe also on the B32 or B64. So there's actually some choices. So every platform defines some set that you can use. So now you've got a problem. You have to basically pick which scalars are you going to use to implement this ADT, to represent them. So we call this the scalar assignment problem. You want to minimize the number of scalars, and this is, again, going to be subject to the target machine. So you can't unify like an integer and an object pointer on the JVM because there's no such thing, right? The other thing is you must be able to discriminate all the cases. So maybe there's not an explicit tag. It's easy to think of it as an explicit tag to discriminate the cases, but there may be other means by which you can discriminate them. So the question is, like, if we have this definition here, so there's four cases there, they have fields. So this was a 28-bit integer. This is a 32-bit integer. Here's another 28-bit integer. And you need to put a tag there. The tag has to be at least 2 bits. So it's effectively, they call them sum types for a reason. They have to add up to something. And so the easy way to do it is the greedy algorithm is you effectively start with the first case, you map the tag to some scalar, and then you map to each of the fields to some scalar, and then you have an intermediate solution, and then you go to the next case, and you do the same thing, and you try to reuse the scalars that you've already used for the previous solutions. So the greedy algorithm will just keep adding more scalars if they don't fit. So there's a kind of a unification going on. If you can unify with the previous scalar, you will do it. And so that's how you end up with tag pointers. So if you have a tagged representation like R32 available, and you have already ref, maybe you can reuse the ref as an R32. So this is the basic algorithm. There's also other ways to do this too. So for example, imagine that you had a ADT which is effectively defining either a string, which is exactly one string, so it's this, or maybe it's an array of strings. So those are both represented as objects on the heap. So the object on the heap actually has a tag, a runtime tag. So maybe you don't actually need to have an explicit tag for this ADT. You can use the tag in the indirection. So in this case, you can unify these two to be ref. And so you can represent this ADT, and you don't actually have to have any additional information. You don't even need tag pointers. So you can even do this representation on the JVM. But there's a wrinkle, which is the pesky null. Virgil has null, strings can be null, and so you need to be able to distinguish between a case string of a null string and a case more of a null array of strings. So that's actually pretty easy to do. You can just consider them to be additional cases, and they can unify, and maybe you actually have a null, like 2 different null objects, and so you can tell whether you point to null object A or null object B, and then still use ref to represent all of them. But that's not enough. You saw before that we had this case where we had 28-bit integer and a 32-bit integer. It's kind of a weird thing. Why would anybody do that? And the reason why is packing. And so that's the other part of this paper, which is packing ADTs. So we ended up with a pretty suboptimal solution where we had like 3 B32s for that one example. And there's sub-word quantities, actually, so we should be able to pack them together. And usually the tags are small because the tag is like the logarithm of the number of cases that you have. You only need a couple bits. So maybe we can pack them into the same word. There's also another really good reason to be able to pack ADTs, and that's that some ADTs actually don't come from our program. They come from the outside world. They come from some network packet description or something, again, in the same kind of vein as like the kernel demands that you put your data in this format. There are data formats that are similar. And here's one. This actually maybe isn't such a strict requirement because this came from the compiler, the Virgil compiler. But this is how some of the source information is represented in the backend. It's packed into a 32-bit word. I did this by hand, late night, mad hacking and like bit mask everywhere. It's terrible, right? That code is like full of bugs, and I almost lost my mind debugging it. I wish I could have written this, because what really is going on is that a source entry is either an extended one, or it's some words, or it's a line column, and ADTs are the perfect thing to describe that. And if you notice, they're all sub-word things. This is 18 bits. I really squeezed them down. This is 18 bits. This is 11 and 8. And what the packing declaration gives you is the ability to lay out the bits exactly how you want them. So here we effectively use a binary literal. And then in the binary literal, of course, you can put 0 or 1. But you can also put a character. And the character is the name of the field. that you're using a bit from. So for example, here, we're effectively encoding the tag as 1, 0, and then all the E's from this E field. And we just use the first character of the name because that corresponds to a single bit. If you have two fields with the same name, it will complain at you, and you should rename them. And similarly, the interesting case obviously is the one at the bottom. We have two different fields. There are 11 bits in the first one, so we need to put those here. Unfortunate choice with L versus 0 and 1. But then you can put the C. And the underscores don't mean anything. Those are just separators. So the compiler will basically say, all right, you have given me a complete description of where you want to put the bits. You don't have to deal with it. I will do it for you. The issue is that you need to be able to actually discriminate them at runtime. So if you gave packings that were ambiguous, when you try to take the memory word and interpret it, which case am I doing when you're doing a pattern match, you should be able to decide. And so the compiler has an automatic algorithm, which is actually part of the paper that Jens and I wrote together in the Declarative Approach to Machine Code Tools. You basically build a decision tree, because you can take the concrete bits and you can take the set of patterns and you can recursively divide them. It's so easy that it was left as an exercise to the reader in the paper. But it's harder than just arranging the bits because we have pointer fields. So for example, maybe we want to make use of the fact that the runtime system can do tagged pointers. And so maybe we want to be able to pack primitives in with the case where there's a reference. So in this case, so maybe we're representing values in, for example, JavaScript. JavaScript engines do a lot of optimizations around small integers, which are 31-bit in size. And then effectively you have two cases, which is it's either a small integer, which is 31 bits, or it's an object. And then everything which is other a JavaScript value is some subclass of object. So what this ADT gives you is the ability to declare a packing where there's effectively a tag bit here. And the idea is that the other case, you don't say what its representation is. And if the compiler can find a solution to that, then you effectively get a tag pointer out of this. So then in your code, which you've already written to use values throughout the runtime system, you're just going to do pattern matches. You never have to deal with smize. So I worked on V8 for a long time. There's an endless array of code that does this. There are utilities. You can do that in C++ using C++ arcane rules, but now you actually have a mechanism to do it in a nice language, and you just let the compiler do it for you. You may want to under-constrain the specification. We saw an under-constrained one there too, but maybe you don't want to write out every single bit. For example, it's kind of tedious to write those binary literals and make sure you got exactly 11 bits and they didn't overlap and things like that, and deal with tags. So there's some underspecified layouts where you effectively make the compiler do some of the work. So in this case, we've got a value, maybe there's an A case, 12 bits and 13 bits, but we actually don't care. We just want the compiler to put them in the same word. In that case, you can say packing X, Y. And that just means I want X and Y to be in the same word. If you want them to be in different words, maybe you can say A, comma B without the parentheses and just says, separate these into two words. I don't care how you do it. I just want a packing where there's two words in the end. You can also use question mark. Any place where you have a binary literal basically says, I don't care about what that bit is. You can choose it. You can use it to represent. You could put, for example, tag bits in there. So the compiler effectively has a problem now to solve. And that turns out that that problem is NP-complete. So if you have a general graph, an undirected graph, you can encode it in adjacency matrix into the bits here. I won't get into the construction of that. It's actually pretty straightforward, but the color is the question marks. So you just ask the compiler, I need to discriminate these things. These are the nodes actually that you want colors for, and it is going to pick them because the colors are the assignments to the question marks. There's one little detail there. You have to round it up to the next power of 2, so you have some cases that it's not allowed to use. And so this is actually fully general. So graph coloring, you're not going to have the compiler solve every packing problem for you. It's just not feasible. So what happens when that case occurs? So you wrote some packing declaration, and there's some ambiguity, and it just doesn't work. There's just no way to do it. And obviously, this should report some kind of an error. It's an NP-complete problem. How hard should it try before it finds a way to disambiguate? I don't know what the answer to that is. I think probably, we didn't actually solve that problem in the paper. It should probably be like, maybe it will try n squared. And then if it can't do it in n squared, it'll say, please, you give that to a SAT solver and then come back to me. So I think that's probably what we'll do in the end, is that the compiler will complain if it can't do like the sort of specified n squared algorithm, and then you go off and ask the SAT solver to do it for you. In practice, people aren't doing that crazy things with packings. They need that level of support. But this language is also great because it's bidirectional too. So I can write the packings that I want for my ADTs, but the compiler can also tell you what its packings are. So for example, I don't know what the target architecture is, but when I compile to x86 64 Linux, maybe I want to know what the runtime system does with pointers. So what is the representation of a pointer on that target? The compiler can just print it out for you. So this would be, for example, how are pointers represented in 64 bits? Well, actually, we're using a pretty small heap, so maybe they're all actually upper bits are 0, and then it's going to be all question marks. And it can also tell you they're all aligned, so the last 3 bits are 0. And so then you can write in your packing declaration that something that does not have zeros in its lower bits, and those are therefore discriminable. Similarly for nulls, nulls might be represented slightly differently too. So maybe we have some part of the heap, like maybe the lower, some part of the memory space is not actually part of the heap. So like maybe the low 1 megabyte of memory is not part of the heap. And so we can encode many different kinds of null things or SMIs in that range. And so they're going to be distinguishable from null pointers. IEEE 754 is the thing. So float has a specific representation, and that's what it looks like. So you can ask the compiler, hey, tell me what IEEE 754 is, and it'll tell you exactly how floats are laid out. And so you don't have to do the bit arithmetic yourself. So you might actually have to do a little bit of tinkering, because for a given target, maybe you have a tagging scheme in mind, and your ADT works on one target, but it doesn't work on another target. So you might have to relax it a little bit. So in our case here, where we're trying to do SMIs and refs, maybe we can't get 31 bits. And so maybe we back off a little bit and say, we only want 30 bits, and you get a question mark at the end. The compiler can use that. So we've implemented layouts, so that's stable and used in production as much as Virgil is a production language. But those are used in Wizard and other things. Unboxed actually works for manual annotations. It's respected when possible. There's really not good feedback. It basically, if unboxed doesn't work, because your ADT could be recursive, it could also be closed over. Closures have a special representation that where unboxing doesn't work. It may not tell you that it didn't unbox something. It'd be nice if it did. We're still using the simple greedy algorithm. It's not optimal. And the packing work is kind of a work in progress. So a lot of that is science fiction, what I said, but that's typical for research papers, right? And that's all I got. Thank you.
What's a SMI?
Small integer.
I love the compiler problem. I wonder, is some of this like going to make it into WebAssembly one day?
Oh, that's a good question. So WebAssembly has like a second level type system in the component model. I'm not sure if you're aware of that. It is effectively like a data interchange language, and it has, I'm not sure if it has quite ADTs, but it has records and other things. So core WebAssembly has a low level type system, which is 32-bit and 64-bit machine level types. It might make sense to actually have it in the second level type system in this component model.
That would be cool. Okay.
Great. So with mutually recursive data types, for instance, you will have multiple ways you can, you might have multiple ways you can choose the unboxing. Have you, as a support for those things?
Right, so we thought about that too. So what you're referring to is basically you can have recursion through a specific field, and you may want to unbox that case but not that field. And so it may be that we should have the unbox annotation be allowed to be applied to fields, and that basically means box this field but not the entire chain, and you don't have to box the entire ADT. Yeah.
Okay, so right, I wonder if one could rethink a programming language would be designed from scratch. What would be the ideal set of constructs that avoid all sorts of challenges that the ones that the languages that do become popular face, right? Have you tried this in sort of reflecting on Virgil's design?
I
have that liberty, right? I don't think the developers of Java or Rust have that liberty, but you would.
Yeah, I mean, that's a really open-ended and interesting question. I think I mostly thought about how LLMs might be beneficial if they could translate other code into Virgil. So not everybody knows how to write Virgil code, but you want to interface with that code. I haven't thought about what an LLM, I've tried to teach ChatGPT Virgil. It actually, I mean, it's read like all the publicly available stuff. It really wants to write Python syntax when I tell. So it was able to write a mostly syntactically correct like pandemic simulator. I don't know why it wanted to write a pandemic simulator. I asked it write a program that simulates something, and it was like spread of disease. I have no idea why it did that, but it wrote, it wrote pretty decent Virgil code. And then after it reached this context window, it went back to Python. Maybe you can feed in the grammar to the LLM and you can have it do magic PL stuff. That stuff is really exciting. I don't know where the future of PL and AI goes. I haven't really thought that through. Thanks for your question, though.
Okay, I think that is the end of the session. Thanks.
Sorry?
Working this whole time.
Sorry?
It's not been working.
No. Hello?
He has to change the screen, that's all. Okay, there we go.
Okay, welcome everyone to the afternoon session of JENSFEST. It's my pleasure to introduce our second keynote speaker, Vivek Sarkar. He's the Dean of the College of Computing at Georgia Tech. And before that, he was Professor and Chair of Computer Science at Rice University. And even before that, he did many wonderful things at IBM Research, including JAX RVM, the X11?
10, yeah, 10, yes.
X10 project. And I could keep going back and it would keep being as impressive, but I'll stop now and let Vivek speak.
Sure, thanks Mayur, and what a pleasure to be here. And so glad, I mean, there are wonderful, many wonderful photos of Jens. Well, glad to find this one. It seems to work well. So, yes, Jens, the ultimate PL Renaissance man. So some of my connections with Jens, and only some, I'm sure I'm forgetting a ton. But one was, when I was at IBM, Frank, who's here, Frank Tipp, there he is at the back, was in my department, and he would update me on his work on JAX and the key role that Jens's work and the work the two of them were doing on call graph construction. And that in turn also led me to read Jens's book with Michael Schwarzbach and kind of just get more acquainted and all of that. So that was like, oh yeah, because we had so many static analysis projects going on and we were moving into Java. So marrying it with type analysis was really important. Then I remember a few visits to Purdue when there was this very vibrant community, right, with Jan, Jens, Tony, Suresh. Well, there was a coffee shop where we would just meet there. We wouldn't meet in the department. We'd spend the whole day in that coffee shop. What was it called? I forget, but anyway, yeah. I found this community for me at IBM when we were kicking off projects like the X10 language that I'll talk about, the JAX RVM, later when we were doing Eclipse and the Eclipse Innovation Grants. This gang of four was always a great sounding board, always very enthusiastic, and also giving us good feedback about how things would be received by academics and so on. And one example of that was the encouragement, especially that Jens had for us with the X10 language project. And in fact, his student, Christian, who's here, was an intern at IBM and was a primary contributor to the original, there he is, the X10 project. And then I will say a little bit about the paper that Jonathan Lee and Jens had on featherweight X10. And then there was this concurrent collections programming model led by Kat Nobe, and it played a key role in our NSF Expedition Center, which when I was at Rice, we were working with UCLA, and Jens played a key role there that I'll talk about. And then we had so many other interests, like register allocation. There was work that Jens was doing with his student Krishna, who's over here, and Fernando Pereira, and so on. So it's really great to have all these connections. So what I thought I'd do for the talk is just do a deep dive on one of them. Well, where is this going? About the featherweight X10 paper. So Jens may not be aware, and many of you may not be aware, even though my background is more high-performance computing and compilers, the grad students twisted my arm at Georgia Tech to create, Chirun is aware because he's my colleague at Georgia Tech, create this class, CS6390, which is programming languages, where we got a lot of material from Bob Harper, Benjamin Pierce. It was, STLC, all that good stuff. And towards the end, I actually do a lecture on featherweight X10. So, in fact, many of the class projects, because people could choose what they want, ended up being extensions of featherweight X10. So the background was we at IBM, this is with my good friend Vijay Saraswat and others, had created this language called X10 that was presented in UPSLA 2005 in the onward track, I remember. And it was really focused on how to make distributed parallel high-performance computing more productive. And there was this notion of places, which is now getting increasingly important with heterogeneous computing and so on. And this locality rule that all data accesses have to be local. And so that was the paper. And there were two of the key constructs that we are still using in my group's research is this idea of async and finish. They nest very nicely in a grammar that Jens then formalized in the featherweight extent paper. So async around any statement indicates that that's an asynchronous execution of that statement. The implementation is free to execute statement 1 before or in parallel with statement 2 or after statement 2, it's asynchronous. And then there's this finish construct, which is also lexically scoped, unlike a barrier or a wait operation, where everything in the scope of finish, you can only proceed beyond the scope of finish after everything in the scope of finish is completed. So you can nest asyncs and finish and so on. So that was, we felt, a more structured way to approach parallelism. And one of the motivations was you can get some guarantees. So, if you can create threads in other languages, you can start them, you can wait on them, but if you have these low-level primitives, and this is a very trivial example, it's easy to create cases where you have deadlock, thread 1 waiting for thread 2 waiting for thread 1, and so on. So the intuition we had was that in extend, because of the nesting structure, you should be able to establish deadlock avoidance, because the only blocking operation was finish. So, to have a deadlock, you need to have a cycle of finishes. But if you think of the execution proceeding of the tree, the weighting only goes upwards in the tree, so you cannot create a cycle. That was our intuition, and it was a correct intuition, but the property still had to be proved. And so now in my class lecture, I talk about different ways of verifying programs. One is that you have a class of programs, so if you have parallel programs that are restricted to only using finish and async, then you can prove that any program in that class will never deadlock. Then we've got other kinds of verification where for a given program or for a given program and given input, but this is like the universal one where a subset of features gives you some guarantee. So this deadlock avoidance is a great example. So this is the work that Jonathan and Jens did, where they created a featherweight language, which is Turing complete actually, and with the two parallel constructs, async and finish. So here's the grammar, and you can see they have iteration, but you can see async and finish showing up over here. And the semantic structure, which is very elegant, is a state is a program, and the array, which is a proxy for the global memory that could be accessed by all the tasks, and the tree. And the tree can represent a sequential composition over here, a parallel composition of subtrees, or a unit statement, or the completion of execution. And so in their paper, they had the small step operational semantics, where you could take a step in this triple, and the program is the same, but then the array could be changed to A prime, and the tree can be changed to T prime. And so just some of the rules, like over here, if you can step from T1 to T1 prime, and you have T1 followed by T2, then because of the sequential thing, you have to make progress in T1 first. So, or T1, you don't have a corresponding rule for T2 because you have to completely execute subtree T1 on the left of the sequencing operator before you go to the right. In the parallel case, however, you have an option. If T1 can step to T prime, and T1 is executing is logically in parallel with T2, then you can have the left subtree step to prime, or you can have the right subtree step from T2 to T2. So you can choose how to grow the subtree as it executes. You can take a step in the left subtree, the one on the right, because the two subtrees are logically can execute in parallel. And you have many possible executions, right, depending on how you make the choice. So that I thought was a very elegant way to capture the essence of parallelism. And of course, there were rules about the standard individual statements. And here was the program. We had the intuition, the theorem. This is what we were waiting for, that Jonathan and Jens came up, is that for any program state, either you've completed execution, it's basically a progress theorem, or you can take a step. And that's essentially saying you cannot create deadlock with finish. So that was wonderful. And then in my, just to flesh this out, when I talk to students, then I say, well, that's great when you have certain constructs like finish and async, and no matter what parallel program you write with finish and async, you're guaranteed absence of deadlock. But there may be some other properties that are not guaranteed that are specific to a program. And this is where type systems come in, because then if the program is well typed, you can get some guarantees over there. And we've had the opportunity, inspired by some of Jens's work, to work on this. And these were colleagues at IBM, Satish Chandra, Vijay Saraswat, and a collaboration also with Ras Bodick on type inference or locality analysis, because we had this rule that you can only kind of like dereference a pointer if the data is local, but you can pass global pointers around. So you have to make sure when you actually, I'm saying pointer, but it was really an object reference, that the actual dereference occurs when you're at the place where the data is located. So this type system did that. We've done some work that appeared more recently in eCoop on a linear type system for promises and permissions for race-free parallelism. So this, these were not directly influenced by Jens, but indirectly when I started learning about types based on Jens's work way back when I was at IBM. And then, of course, then what happens is that what if you don't have a type program and you want something, and then you can try to prove something for a given input. Even that is strong, because then for parallel program, you're proving it for all possible parallel executions of the same input. And for the same input, there can be many interleavings. And we've had the opportunity to do some work over there with futures and deadlock avoidance with futures and so on. OK, so that was one bit of a quick summary of some very major influence that the work done by Jens and his students have had on us. And so then I would basically summarize it to the students in my class, saying that you can have these 3 levels of verification for a whole class of programs, or a given program, so all input for a given program and input, but for all executions. And the lesson that we learned is the structured parallel primitives can really help these challenges, because you push more into this first class, which makes it so much easier to have guarantees. Oh, and just so you know, I also inflict on them. In every lecture I do, in the last 10 minutes, they do an in-class worksheet collaboratively. They're not graded, but they have to turn it in. So they can totally work 3 or 4 people, and someone can write a solution they heard from somewhere else. It's just like, did they grok the lecture or not? And so I gave them a featherweight extend or an extend program and said, OK, start evaluating it. We gave you a couple of steps. Like if you start with the program, here's the sequence, and do the step-by-step, and this is the solution. So they have to kind of go to figure out how one possible execution is not the only one with parallelism. And then I asked them, is there only one possible execution trace? And no, but they have to think about the fact that the parallel rule means you can choose one or the other. So hopefully they figure that out. And is there only one possible state? For this program, it turned out there were no data races, so it ended up being determinism. So even with this, I mean, this is to reinforce. I'm sure many of you have this experience too. The featherweight language like this can be a great pedagogic tool to help the students understand many of the fundamental concepts here. OK, very briefly now to wrap up. I'd mentioned the NSF Expeditions project. It was really great interdisciplinary projects where we had colleagues from computer architecture, software. Denny Aberle is a radiologist, MD, and so on. Compilers, good friend Sadayappan. So, and actually Jens was critical to connecting me with Jason Kong for participation in this project. I ended up playing an associate director role with Jason as the director. And there we had this model called concurrent collections, the one I mentioned earlier, led by Kath Nobe. And what we were able to do is use it as a way to schedule on a very heterogeneous platform. This is like 12 years ago, or more than, where we had a hardware prototype with CPU, GPU, FPGA, and you had this notation where you could create tasks that could be scheduled. And in fact, you had multiple versions of the same task. You could have a CPU version, a GPU version, FPGA, and there were scheduling advantages both in execution time performance and energy savings by choosing one or the other. But getting back to concurrent collections, the idea here was it tried to capture the essence of parallelism in a safe way, but as a coordination language without worrying too much about the sequential language within the task. And the coordination was in the form of a data dependence, whether like a producer-consumer, kind of like a key value tag, that's what a data item was, and what was called controller-controllee, where steps could be created asynchronously. So basically, you're capturing the essences of program dependence graph, data dependence, and control dependence. And we had different forms of notation, a textual one that could be processed by a compiler, what we do in PowerPoint, what we do on the whiteboard, but the same idea. And one, again, and this was really synergistic with Jens's work on featherweight extent, we needed a determinism property, a confluence property, because there's no shared memory, so there's no room. So we intuitively knew that all possible execution should lead to the same final state. But again, it took the collaboration of Jens to establish the main theorems over here. So we had this paper in the Scientific Programming Journal, and then here was the main theorem of determinism, which was, again, very, very helpful to us. And there are, thanks to that, we established determinism. We're no longer working on CNC execution, but I'm just saying, if anyone's interested, there's some other conjectures we have where the proofs are pending, like an idempotent one. You execute 2 copies of the same task, you should get the same answer. Parallelism one, meaning the semantics, if you execute things in parallel or sequentially, should be the same. That should be easier. It should follow from the determinism property, I think. Okay, so I think it's a good time for me to wrap up now. So what have I learned? Well, our community is much richer with you, Jens. And let's see. So I found Jens to be a real kindred spirit. We didn't really grow up in the same research community. I was more on the high-performance computing side. Jens, of course, in the PL Foundation side. But we could talk about any topic like parallel programming models, register allocation, more recently quantum computing. But as was alluded to at the start of the talk, and this was the 3 sides to Jens, so we've had really great discussions, especially when I moved from IBM to academia, about how academic administration works. And I remember even walking, when did we have that retreat on that ship, the Queen Mary? Remember, we just did rounds and rounds on the deck talking about some of this stuff. And more recently, Jens and I, along with many others, serve on the ACL, not many others, like a dozen others, serve on the ACM Council, and we've been having some discussions about some, very important topics related to the role of governance and volunteer leadership and so on, which has been incredibly valuable. And I think your intellectual curiosity is inspiring, and somehow I think it's always great to have Jens in the audience. So one reason I accepted this invitation was I knew he was going to be in the audience. I remember Jens was in the audience when I gave the Extend talk in 2005 because he had some question. The SSA workshop that in France that we had gone to, where I was talking about Ray SSA. So having Jens in the audience when you're giving a talk is really wonderful. And this is why I truly think of you as the ultimate PL Renaissance man. So thank you.
Many thanks. I want to say I treasure the memory of when the project at UCLA and RISC was going on. You would come out, visit us many times.
Yes.
And I remember the many times we would walk to the poster session together or drive to the airport together and something, and just have a chance to talk.
Yes.
Really very treasured memory.
Same here. And actually, I usually depended, this was pre-Uber, so Jens was the one who would give me the ride to the airport. And thanks to LA traffic, we had lots of time to talk. Okay. Thank you.
Thank you, Vivek.
There you go.
Do you want to try to get Fernando? Okay, let's do that. The next talk is by Fernando Pereira, who was Jens's PhD student, but it is a remote talk, so just a moment. I have others who want to talk for 5 minutes. Shall I move on to them? Because you are not able to get him. Is that okay? How about, are you ready? Okay, so yes, check 1, 2. Fernando, can you hear us? Hi, Fernando, can you hear us?
I can hear you. Yes, I can't see you.
Okay, great. Yes, we can hear you as well. I'd like to say that, add one thing. Fernando actually has been the driving force behind this whole event. It wouldn't be happening if it weren't for him. So big thank you to him. I also learned that, I thought,
I'm very honored also to be like kind of a grandchildren, PhD grandchildren of Peter. So to me, I'm very happy with all that. Anyway, I prepared, I submitted a small paper to JENSFEST as a homage. So I'm gonna present this work. Let me share my screen here. You guys tell me if that works. So let's see. I had sent a video as well, but maybe presenting it live would be better. So let me just make sure that I can get the presentation. So, you guys, I know that's not very easy, but you guys can interrupt me anytime you want in case there are any questions. So this paper is called the essence of the flyweight design pattern. So this is a work that I did with Caio Raposo, who is a student, a master's student who I advised here in Brazil at the Federal University of Minas Gerais. So what's the story of the paper? In 1998, Jens was working on that paper, the essence of the visitor pattern. At the time, I think Jens was a few years after that. I took the compiler construction course at UCLA, and Jens was, the teacher at the time, the professor who was teaching the course, the instructor. And then he had all this fancy Java thing that would synthesize those visitors that were super cool, actually. And then at the time, I think Jens was a great fan of the visitor design patterns, a way to process programming languages. So in a way, I mean, the visitor, it brings to the object-oriented world something that's very common in functional programming. I mean, you want to fix the types, and you want to be able to vary the operations that you can perform on those types. So this is what we get with visitors. So essentially, we can, here's an example of a visitor in Python. So we can, define methods for all the types that we have in our hierarchy of classes. And pretty much what visitors are doing is making something that's already native on a functional programming language. I mean, you have data types, this closed world. Like in an object-oriented language, you have this open world where you can always add new types. And then, on this functional-oriented world, we have this kind of closed world of types, and then it's easy to add new operations on them. And that's what we get with visitors. So, I mean, we can do this exercise of looking into those patterns that we have in the Gang of 4. And then we can more or less see which patterns are actually native in depending on the programming language. And you can find many of them. Like if you take, for instance, the strategy or the template method, essentially they are native in any language that supports functions as high order functions, first class functions as first class instance. And then, so in this paper, we did this exercise. Okay, so let's talk about flyweight. I mean, that's a pattern that, people don't really talk much about it. So let's see, how can we make the flyweight design pattern kind of native on an object-oriented programming language? And essentially, I mean, you can make it native if you allow the memoization of the constructor of objects. An object is created by a constructor that's part of a class. If you memorize that constructor, essentially you are kind of adding to the programming language a native way of implementing flyweight. So, but the things that memorizing the constructor of objects may not be a good idea, because objects mutate. And so, if you, I'm not really sure if everyone understand that, but memorization is optimization, where you call a function and then you cache the result of that function, so that if you call it again, you just return the value that's stored there in the cache, the memorization table. So that's an optimization. So if you memorize the constructor of an object and you mutate that object, you are mutating aliases of that object that you created unintentionally, in a way. So just to give an example, I mean, this is a function in Python. I mean, it solves the knapsack problem, but I mean, what it does is really material to this presentation. You can memorize the function with this annotation, the cache annotation. I mean, that's one of the many ways that Python allows to memorize functions. But in this work, we are not really working in Python. We are working on another programming language called Hush. So Hush is a really cool programming language. I will show you the repository soon. It was implemented by one of the students in our university, Gabriel Bastos. So I will talk a little bit more about it. So we implemented memorization in Hush. So, but anyways, the idea is this. I mean, you call a function, you cache its result. If you call it again with the same arguments, you just return the cached result. So in Python, you do annotations, and then in our version of Hush, I mean, that's not official Hush, you have a keyword memo that really actually works on that in the runtime of the language to perform memorization. Our implementation of memorization is actually pretty efficient. I mean, it's likely to be more efficient than one in Python. I mean, at least when you compare similar benchmarks, even though Hush is kind of slower than Python. I mean, it's slower than Python. Hush is implemented in Rust, but it's slower than Python. I mean, it's a scripting language like Python, but slower. Anyways, so we want to implement safe memorization of mutable data, mutable objects into work. There are many ways of doing that, but let me just show what happens if you do this in Python. I mean, we can memorize a class in Python, like just add the annotation of the definition of the class. So in this case here, we have like points, have 2D points, we can memorize them. And then like, if I create 2 points with the same argument, you know, P0 and P1, essentially they're pointing to the same memory because I mean, points memorized now. And then, you know, I can mutate P1. I assign to X, and that's fine. I mean, now P1 has a different value of the X coordinate. However, yeah, that changes P0 as well. And this may not be the intention of the programmer, in the sense that you created an intentional aliasing between P0 and P1. So yeah, now they point to the same memory location. Anyways, so we have implemented safe memorization in Hush. I'll explain what safe means in this case, but just here, publicize the language a little bit. Hush is a shell scripting language. Was created 3 years ago here in our university. It has syntax that's very similar to Lua, which is another Brazilian language. So I mean, kind of similar. Similar in syntax, but not in purpose. So Hush is strongly typed, meaning that the programs are always, you know, well behaved if they are well typed. But it's dynamically typed though, like Python, Elixir, Lua itself, Bash, and this kind of languages. It has a garbage collector, and actually implementing memorization for the garbage collector was pretty interesting. And it has first-class functions. I mean, this will be important to us in this presentation. Anyways, it's kind of popular. I mean, if you go to, I went to the GitHub 2 days ago, and then I had like more than 600 stars, and has users like forks, issues, people submit issues. I think it's a very nice program language with a clean syntax. So I mean, if you guys want to take a look, there's a link of the repository right there. Anyways, so something interesting about Hush. I mean, Hush doesn't really have classes. Yet, you can kind of simulate object orientation. I mean, you can create objects as closures. So I mean, this function here simulates a class that creates counters. I mean, that's the syntax for dictionaries in Hush. So we can create this object as a closure on n. It's an argument of the function. So we can have like an attribute that refers to n, and we can have like methods which we associate with atoms, like get and inc. They are keys on this dictionary. So these are methods, and then we return this, and then essentially this function is, you know, is a class creating objects, pretty much. Anyways, and what's flyweight? Again, this is a design pattern. Is a way to reuse some internal state of an object. I mean, you have an object, parts of it vary, but then have like some part that's common among many objects. So this you can implement that using flyweights, this design pattern. I'm going to give an example here. I mean, that's not really an actual flyweight, but it's just a simple way of explaining how that works. So imagine I have students. So students have names and identifiers, and each student is unique according to an identifier. And then we have courses, which are a set of students. You can search students within courses. Of course, I mean, you should have just one student on each course, one version of each student on each course, of course. And then you have this registry class here that works as a factory, like an object factory. So whenever we create a student, yeah, there we go. First you check if you had seen that ID before. If you had, I mean, you know that's saved on a table, like the memorization table. In that case, you return the student. Otherwise, you create a new student and then add that to the table as well. So, I mean, in a way, this is kind of a flyweight. I mean, that's how flyweights are essentially implemented. And in this case here, like students are unique per ID. And then the equivalent version in Hush is the program on the right side, I mean, in blue here. So here we are memoizing the function that creates students, and then we more or less get the same effect that we would obtain if we like with the class on the Python class on the left. So I should be using Python because Python is more well known, but everything here is implemented in Hush. So how we get safe memorization? We have changed the runtime of Hush a little bit to obtain that. So essentially, we use shared pointers to guarantee the following. Whenever you try to memorize an object, you remove it from the memorization table. I mean, it's a very simple idea. I mean, this whole thing is just like an exercise on trying to get the essence of what's a flyweight. So anyways, let me give an example here. I mean, I have here this function that creates points, and then I create P0 and P1, and they have the same arguments, therefore they are memorized. I mean, that's how usually the heap would look like. I mean, we'd have like P0 and P1 pointing to this memory, which is a pair, and then like this memory, X1, X, and Y, and they are on the memorization table. And then in our case, I mean, we will access memorized objects through shared pointers. I mean, non-memorized objects are accessed using, just normal pointers. But then for memorized objects, there'll be these two hops, like one level of interaction through shared pointers. And what do you get with that? If you have a new, reference, like P2 in this case, I mean, reference is now referred to the same shared pointer. And then, like all these pointers, like P0, P1, and P2, essentially, they are kind of like aliases in the sense that they ultimately refer to the same memory, which is memorized. But only P0 and P2 are logical aliases in this case. And then, like, if I modify P1, what will happen is that we create a copy of P1 outside the memorization table. So P1, like this copy, will not be on the memorization table. So essentially, you have like this copy on write semantics. And then, anyways, if you create new objects, they again will be created on the memorization table. So I mean, objects are always created on the memorization table, except if they are modified. In this case, they will be removed from the table. And then in this work, we have like a formalization of these properties using Alloy, the Alloy specification language. So that's something that Kyle did very nicely. So I mean, you have a number of properties that he managed to demonstrate using Alloy. So for instance, I will name 3 of those properties in here. And then the entire Alloy script you can find in the extended version of this work. So first, I mean, the modification of an object, O, will cause a new object that I'm calling O prime to be created. And this object will not be stored on the memorization table. And O will remain memorized. I mean, the original version of O without modification will remain on the memorization table. And O prime will still be accessed through the same old shared pointer. I mean, once an object is memorized in our implementation of Hush, it's always accessed through a shared pointer, even if it's modified. So I mean, when you generate code for Hush, there is a small if-then-else there for every object. I mean, is this object memorized? If it is, we implement access through to load. To have to load first a shared pointer and then whatever the shared pointer points to. Otherwise, we access the object using just one load. So, but what's interesting is that this implementation, it doesn't really seem to incur on any noticeable performance penalty. At least we haven't really seen anything like that. I'll show a few experiments. So, I mean, in the extended version of this paper, we have 4 research questions. In this paper, I will go briefly over 2 of them. So first, I mean, the first question is just to demonstrate that our implementation of memorization is not really strong, man. I mean, it's very efficient. I mean, you get, those performance boosts, like you can make an exponential function run in linear time with memorization. So, if the function is referentially transparent. But I think that our benchmarks, like the object-oriented benchmarks, it's hard to think about like benchmarks where you get those gains. I mean, so we have this RQ1 just to show that we can get like huge performance boosts out of memorization. And then we have RQ2 just to demonstrate that once we memorize object-oriented benchmarks, the performance penalty compared to unsafe memorization is minimal, okay? And then in the extended version of the paper, we have two more research questions. So one of them is, what's the impact of hashing on the efficiency of memorization? Because, to memorize the objects, we need to do deep hashes. Like, sometimes an object refers to other objects, and then have to compute hashes of hashes. So have to, what's the impact of hashing in this case? And then also, what's the interplay between memorization and garbage collection? In principle, we should not trace the memorization table with the garbage collector. And so there's a trade-off. I mean, if you start memorizing a lot, there'll be maybe like a logical memory leak because the memorization table is not traced. But if you trace the memorization table, then you have a huge slowdown because the table may be huge. Anyways, so on this paper, I will just go a little bit over RQ1 and RQ2. So first thing, is our implementation of memorization efficient? So Kyle has a repository with a number of benchmarks. So 7 of them are like referentially transparent functions. Here's an example. This is Fibonacci. So this function is exponential on n, like on the number of bits of n. You have like an exponential running time. But however, once you memorize it, you get back the linear running time on the number of bits of n. So I'm sorry, not on the number of bits, but on the value of n. So it's like this is like the kind of the hello world of memorization, and so we get like the nice numbers. So what happens if we memorize object-oriented benchmarks? We have 6 benchmarks in the Hush repository, which are kind of object-oriented. We create objects with them. So, and then we have tried 5 different implementations of memorization. So, well, the first is not really memorization, it's just the original Hush. To this day, Hush doesn't really incorporate memorization. So if you go to the official Hush repository and get it and check it out, there'll be no memorization there. So that's the original version of Hush, which is implemented in Rust. Okay. And then have unsafe memorization, meaning that you can get like an intentional aliasing and you don't do anything. You access objects as before, and then you may have programs that may not be really what you want to write. And then have guarded memorization in the sense that you have anything else there. And if you try to modify an object, you stop the program. You trigger an exception, and that will stop the program. So it's still no shared pointers, but there is a guard. You can't modify an object that's marked as memorized. You can't do that. And then you have an implementation of shared pointers as a library. So in this case, we implement like shared pointers. You simulate them using like sets of objects that point to the same, we have sets of objects which are logical aliases, so that in a way kind of simulates the shared pointers. But this implementation will be very slow. If you don't really touch the runtime of the language, it's hard to have an efficient implementation. And then have our implementation with like shared ownership pointers. So we have an if then else to check if an object is memorized or not. If it is, we have to load it twice, like a pointer to get like the final memory that object, that reference points to. So first benchmark, just like a simple benchmark that create polygons. It has a very cheap constructor. So basically, like what this benchmark is doing, like it's taking like a list of points and then creating insert them in the set that defines polygons. And then some at some point to try to see like if a ray crosses those polygons. But anyways, most of the complexity is in creating the objects. But creation of objects is simple. I mean, you create lots of objects, and here like 6,000. And then in this case, I mean, what happens is that we don't really get anything on top of memorization because the constructor is kind of cheap. Something that is interesting is that even though we don't really get any performance improvement on top of the original hash, with memorization in this case, we are not doing much worse than unsafe memorization. So I mean, essentially, like, we're doing the same. If you try to implement memorization as a library, like shared ownership pointers as a library, in this case, yes, I mean, there will be a slowdown, observable slowdown. And this doesn't really vary regardless of the number of objects that collide in the memorization table. Yeah, I'm here measuring the number of collisions and have like almost like 100% of collisions at some point, and the performance is still, I mean, pretty much the same thing. So, I mean, bottom line here is that you have to memorize objects that have like expensive constructors usually. So let's try a new object, a new benchmark. It's time. I mean, using the polygons. It's time to implement figures, and then like have like more complex figures that we can create out of those polygons. So have intersections and unions of figures, and in this case, the constructor is way more complex. So again, I mean, I will be reporting time per number of objects that we create. Using our 5 different implementations of memorization. So first thing, I mean, the original version of Hush will be slower. So memorization in this case will pay off. I mean, you have a faster implementation. And again, there's not really any difference between unsafe and safe memorization in this case. I mean, regardless of the number of collisions that we observe. So I mean, the things that we can implement safe memorization of flyweights in a very efficient way. I wonder if there is someone trying to ask a question there, because I can hear something. Maybe not. Anyways, continue. So I mean, just concluding now.
Can you hear me, Fernando? Okay, yeah, go ahead. Yeah, you were running
Yes.
over time.
Oh, I'm sorry. So just concluding, we have presented a new technique to memorize the functions of mutable objects. Our implementation is available in this repository. And well, there's a lot of things that we can do here, like improving like the interaction between garbage collection and memorization, evaluating the cost of hashing, implementing like maybe memorizing hashes would be something cool. We would like to implement at some point automatic memorization. I mean, but that's future work. So I mean, I'd like to thank Caio. I mean, he did this in his master thesis. He came from the north of Brazil to Belo Horizonte, so it was a privilege to have him here. And I need to thank the Brazilian Ministry of Education as well for funding his scholarship. And that's pretty much it that I have to say. So thank you very much, guys.
Does anyone want to ask a quick question?
I wonder if you guys have questions.
So I think it's wonderful, this thing with the Rust underneath. Is the Rust thing helping you, or are you working totally above the level where Rust has an influence?
Yes, yes. I mean, Rust is absolutely helping us. I mean, we got the shared pointers out of Rust. I mean, that's part of the Rust standard library. So I mean, we could get that into the runtime of Hush because Hush was implemented in Rust. I mean, were it not? Well, if we're implementing C++, we could get that as well, because there is C++ has that as a library, but otherwise we'd have to implement it ourselves. Another thing, I mean, we chose Hush, not Rust, Hush, because it creates objects as functions, as closures. So by memorizing the functions, we get to memorize the class. So we chose Hush out of that. And because it's implemented in Rust, it was easy to implement shared pointers, to add shared pointers to the runtime of the language.
Yeah, oh, that's cool. Anyway, Fernando, thanks for everything.
You're welcome, yes. Guys, academic brothers, other questions? Okay, so I think that pretty much settles it. Is that right?
Yes, sorry, my mic was off. Yeah, yeah. Thank you very much. I actually think C reduce is a misnomer, right? They originally intended it for C, but it is so general purpose that people use it even outside for anything, JSON files, whatever. Which is why you said it was impossible.
Say in terms of the lecture.
Okay, so the next talk, the last talk of this session is by Shuo Ding. Yes.
Hello, everyone. My name is Shuo, and I'm a PhD student from Georgia Tech, advised by Qiren Zhang. Today's topic is based on Yan's previous work in Popo 2016, I think, which was about a thing called a normalization barrier. And this, our talk is going to offer maybe a new perspective to understand the phenomena in terms of how do you define interpreters, how do you generalize results in one domain to the other. First of all, let's review some background and define what is a normalization, the normalization barrier. In the in computability theory, there is a result with a pretty long history saying that computable total functions don't have self-interpreters. The reason of this is because if there is a self-interpreter, you can use that to construct another computable total function, which is not actually inside your list of all functions. So that's like a diagonal argument where you are constructing something that's different from every candidate. This thing brings, in the past, this thing was regarded as a normalization barrier because if you compare this with lambda calculus, where you have a normalization which is very close to termination, it sounds like strongly normalizing lambda calculus cannot have their self-interpreters. Because of this computability theory result, but actually that was not the case. As Braun and Palsberg proved in 2016, F omega, which is actually a strong normalizing lambda calculus, has self-interpreters. Today I'm going to offer maybe a new perspective saying that we can actually change the definition and the setting a little bit to let the original computability theory go through again. So in this sense, F omega doesn't have self-interpreters, just as predicted by computability theory. Everything here is actually correct. There is no contradiction. It is just because we have different definitions, we are viewing things in different angles. So this is an example of a real-world interpreter, which is for Haskell. Haskell is a typed language, but in reality, we are actually calling it from the command line, which is taking some strings as input and producing an output or a type error. In this case, the interpreter, although it is considered typed, in the outside world, it looks like a function from strings to strings because the input is always encoded as string, and the output is either the string representation of the computation result or a string representation of the type error.
But by interpreting the resulting string, you can probably understand which one is a type error, which one isn't, just like in this case. This figure is taken from Brown Palsberg's 2017 paper. Is slightly modified to show the difficulty of defining interpreters in the first place. We first have the conceptual idea of programs, and we have the evaluation result of the program. That is called the small step or big step semantics. And the program is just a conceptual idea, so we should really represent them if we really want to manipulate them in reality. The typical way is to represent them as strings, but you can also do other things like representing them as syntax trees. So we have basically this, like 4 different cases, like the program evaluates to the value, and the representation of the program correspondingly also evaluates to the representation of the value. And in this figure, you can see that conceptually you have a program, but in order to represent it, you have the inductive coder. If you know Lisp, there is a code operation which is basically coding the program to some data representation. And also you can convert it back. This is one type of interpreter that you can have, which is converting the representation of the program to the original form. This also works for the value, because the value is just a special case, a normal form of the program. And for representations, we have the similar represented value. But you can also do this. You just start from the representation of the program and conclude with the representation of the value. This is the second type of interpreter. As we will say in the next few slides, Brown and Palsberg constructed the recognizer in the 2016 paper, while I'm going to present an evaluator for representations of the programs. So that's the difference. And the difference is pretty huge in the sense that in one case, the self-interpreter is impossible, while in the other case, it is possible. This is a review of computability theory, why we don't have universal functions for computable total functions. It's basically a diagonal argument. Suppose that you have a universal function that can simulate every function in C. You just do a self-reference. Because U is a computable total function, this thing formed by composing U and +1 is also a computable function. And then you can do self-reference. Suppose that this is the code of P should be some index here. So suppose that it is J. Then you call P on the representation of P, which is J, and then you get a contradiction. Because everything is total here, you have like a Pj cannot be equal to its value +1. This argument cannot be applied when you have typed representations, because suppose that you have such a typed representation of any term in f omega, which is represented as inside the brackets. Then you suppose you have a self-recognizer for this. And if you want to repeat the non-existence proof in computability theory, you get some difficulties here, because the P itself, which is what you constructed in computability theory, may not be typable. And P applied to the representation of this itself may not be typable. So this means you cannot prove the non-existence as you did in computability theory. That's why
it opens the door to construct a self-recognizer in this case. Actually, Brown and Palsberg constructed one, which is feasible for F omega. This shows that the computability theory isn't that widely applicable. But if we rethink about this case, we are actually assuming a type checker outside of everything. So you are not implementing the type checker inside F omega. You are supposing that there is a type checker that can help you roll out those constructions. So as I showed in before, in reality, we may have a type checker embedded in the interpreter, which actually emits error message on ill-typed terms. So if we take this approach, we can actually put the original computability argument go through, and then we show that in this case there is no self-interpreter. This is what I described. Like in reality, everything is encoded as strings. In F omega, we may not have strings, but we can use Church numerals. And using Gödel's encoding, we can encode any finite amount of information to a number. And in this case, everything is encoded as type T. T is the type of Church numerals in this case. And there is a small caveat here. We choose an encoding to ensure this. The encoding of a Church numeral should be larger than itself. This can help us prove something. It's not essential to the encoding part, but it's essential to the proof part. And in this case, we consider this type of definition, self-evaluators, taking a representation of terms and produces a representation of the evaluation result. And in particular, if the input is not well typed, it should return some error. So this is what I wrote here. In this case, the interpreter has two branches. If the input is a code of a well-typed term, then you just interpret the term to the normal form and then encode it again. If it is not well typed, you return some error message. In this case, you can stipulate this to be your error message. And with this in mind, we can apply the computability construction. This is what we did before for computability. Because in this case, everything is from the Church numerals to Church numerals. You can do this. And there is a helper function apply, which is taking a representation of a term and another term of type T, which is Church numerals. You put the original term of E and the Church numeral X together. Whether this is well typed or not, doesn't matter. You just treat this as a term and then encode it again using the representation function bracket. This apply is like what you do in reality. It is like concatenating two pieces of programs together and then do interpretation or similar. And then you can proceed with this construction. Remember that previously we didn't have the ability to do this because there's it may be ill-typed. But in this case, everything is from numbers to numbers. So you can expand this. And by expanding, you get to this step. And by our assumption that the representation of a Church numeral should be larger than itself, you can get this. So eventually, you still get a contradiction, which is saying that some number is greater than the number plus 1. This is in parallel with the computability result. I think this is the conclusion. I'm trying to complete everything before 3:30.
the key takeaway is that we have 3 seemingly different results, but they are not really contradictory. They are just viewing things in different angles. And in particular, the computability angle and our angle that I just described, those two are pretty similar. They are just trying to include errors also in outputs, including type errors. But if you do, if you don't do this, if you just avoid ill-typed terms to evaluate in any case, that brings you to this case of 2016 paper, total self-interpreters are possible for alpha omega. So I think the conclusion is that when we talk about such possibility or impossibility case results, we should really make sure about the setting and the exact definitions. So because for different definitions, you may get totally different results. Yeah, thank you.
Very impressive. I have a question for you.
Sure.
So your conclusion for a while seemed tied to F omega. So are you saying any type system, strongly normalizing type system for lambda calculus is still impossible?
It actually requires some small amount of expressiveness. You have to you should be able to express +1 and church numerals in those.
Okay, so let's say F omega and more powerful than that.
Yeah.
That's definitely enough to express those things. So
yeah.
It's not possible in any of those systems either.
Under this definition, it's impossible if we embed the type checking into it.
So it's in a way a very generic result. That
yeah.
The type system just has to satisfy a couple of conditions and then
yeah.
this kicks in a lot. Okay.
Thank you.
Any other questions? No, let's thank the speaker.
Now, sort of on. All right, so earlier today, Peter asked if any of us were in the room when Jens gave his talk at UPSLA in 1989. And I raised my hand, and I don't think anyone else in the room raised theirs. I was a PhD student at the time, and I was actually quite impressed by the work that Jens was doing. It was a little bit outside of my area of interest. I was much more focused on programming language systems than programming language semantics and theory. But of course, I was interested in object-oriented programming languages, and his treatment of inheritance was really the breakthrough result there. Now, I want to speak to a few things about Jens. Courage, fearlessness, collegiality, and legacy. I first met Jens probably when you interviewed at Purdue in 96 perhaps, or 95, no actually 95. I was a freshly minted assistant professor wondering what the heck I was doing at this university where I was the only person working on programming languages and feeling very, very lonely and wondering if I should have perhaps chosen otherwise than Purdue. So Jens interviewed, and that was a very exciting time because suddenly here was the opportunity to have not just one person in PL, but a second person. And of course, Jens came that year, 96, to start as an associate professor at Purdue. I remember meeting him the first weekend that he arrived in Lafayette. And what does a Dane do the first time they arrive in a new place? What is their mode of transport? And if you've ever been to Copenhagen, you'll know that everyone gets around on a bicycle. So Jens's first purchase when he was in Lafayette was I took him to the bike shop and he bought himself a bicycle so that he could get to and from his office on campus. And he was living in an apartment sort of out in the cornfields. So I'll speak first to courage. Shortly after his arrival, Jens arrived to work with a bandage on his hand. And I said, what happened?
And he said, "I've been shot." I said, "Welcome to Indiana." It turns out I think you were on some late night expedition home from the lab, and some hooligans driving down this backcountry road decided they were going to take a pot shot at Jens on his bike, and courage in the face of fire, under fire, courage under fire. So it was a BB gun, yes it was. But there was blood and there was a wound. So courage under fire. Anyway, Jens stayed. He decided he wasn't going to leave as a result of having been shot in the cornfields of Indiana. And he stayed on as over the years we built up a group of PL researchers that I think it's at one point numbered approximately 8 of us. Vivek reflected on a few of us who were there at the time when he was interacting with Jens at Purdue. Jan Vitek was in the room. Where's he gone? He's not here. And others. And that was a really pivotal time for the PL activity at Purdue. It really launched a whole bunch of different activities, my own included. I was relieved suddenly not to be the only PL person there, and felt that there were opportunities now to actually build and grow something really special. And Jens was instrumental in that, because he ended up hiring people like Suresh and Jan Vitek and Patrick Oigster, and who else was there that were in the mix that you hired? Others came after. Okay, but that was certainly foundational. Fearlessness, and I'll speak to Ben's talk earlier today. I think I was still an assistant professor at the time. Ben comes to my office and says, I want to change my direction on my PhD thesis. I want to invent a new programming language. And my response to him was, "You're crazy. No one ever gets ahead in academic research by just coming up with a new programming language out of thin air." And particularly given that I was focused more on the implementation side, the last thing I wanted to do was think about a new language and how to implement it, let alone think about how to make Java a language that we could actually use and find useful. Yeah, Martin Odersky's, well, but you're putting yourself now in the class with Martin Odersky, so that's good. So fearlessness, Jens at that point was on his way to UCLA, and fearlessness in taking Ben on to do this work on Virgil, where many other advisors would have balked, and in fact I'd balked. So my mistake, Jens's win, and Ben's win of course as well. So I also want to just speak to that legacy piece. So Jens has not just been a colleague in the workplace, he's been a colleague in the community. He's been a supporter of programming languages across all of the things that we do, and I would like to commend his leadership in our space, which has been selfless. It's not just been about his own research. It's been about the research of others, and it's been about the community in which we operate, the ACM family that we have here in SIGPLAN, and the opportunity for all of us to work in this wonderful domain, which is, I think, continues to be vibrant. We're not all doing AI, we're still doing PL research, and that is a fantastic thing, and I commend Jens for the leadership he's shown in that space, and I would like you all to thank him for that contribution.
So Tony, many thanks. I also want to say that I always thought about it as you championed that I moved to Purdue, and together we championed that we hire Jan, and together all 3 of us championed that we hired Suresh, and then that we at least down the line, some of the names that you mentioned. It was really great times and a total highlight of my life. I often say that my Purdue days was the most social time in my life, because we would go out to eat and have things together so many times. I've been to your house to watch cricket, of all things, right? Which is a great memory, and so many others. So many thanks.
Again, after the coffee break, and one more announcement: we'll have a group photo at the beginning of the session.
Great, thank you. Right. Good afternoon. Hello, Jens, specifically to you. And when this idea floated, I thought I'll share a few stories. So today in the morning, Todd said, among many other things, Jens is a comedian, but I feel it's a comedy which has very meaningful message. Pretty much many times in my interactions, when I've asked him a question, in comes a story. And the first one, I remember, I was struggling with a lot of time management issues. I was thinking, oh, there's too much of this, too much of that, and so on. And then suddenly I find, hey, on Jens's webpage, there is a new note that he has finished his MBA, right? Along with many other things. I said, what do you do? I mean, how did you manage? And then he told me a story. So the story goes like this. A shepherd was living in a lonely place. He was very busy. He had 50 sheep, right? And then suddenly his uncle shows up, comes to him and says, look, I have to go to Mecca to offer my prayers. You have to take care of my 30 additional sheep. Shepherd says, I'm too busy. I just can't live. I mean, I'm having breathing trouble just with my 50 sheep. You are giving me 30 more. Uncle says, nothing. It's God's call. Goodbye. Right? He leaves his 30 sheep and goes. And uncle comes back after 3 months and thanks the shepherd, takes his 30 sheep and goes home. And now the shepherd finds that he has lots of extra time. Right? Yes, I mean, I have found it to be a very important light in my life. And I have probably told this story many times to many people. Right? Right. Here is one more. I still remember we were taking, I think, Principles of Programming Languages Popul course at Purdue. And as part of one of the things, Jens talks about type-safe method inlining. The thing that I really found exciting in that is it's a very, inlining is such a fundamental transformation, and how some very simple steps that are taken by many was breaking. And the light in Jens's eyes saying, hey, wow, this is a very common, important problem. It just breaks. There is a way to fix it in a provable manner, right? And the excitement and the impact. I mean, I found it kind of very, it's kind of imprinted in my mind. And a very similar excitement we had was in Java, when you have applications which depend on libraries which are running on one place. You compile in one place, you run on another place. So the libraries could be very different. So what we said is, hey, can you take the application code, analyze it on the client machine, bring the analysis and the application code onto the target, get the analysis results on the target machine, combine them somehow, right? Combine them without losing any precision, right? It's a problem that has been pending for a long time that people knew, but somehow it was not working out. We were very happy, and when we got it solved, it was one of those very high moments that I feel very proud about. So being able to do something which is very useful, which looked kind of should have been done, right? So this was one second story. Here is the third one. This is, like Mohsin said, probably a personal one. I'm not sure if Jens remembers, but I do. This was immediately in my first year towards the end. And I was kind of, Jens is coming out of a classroom, and I said, hey, Jens, I want to talk to you. I said, look, Jens, you keep saying, hey, it would be good if you do this. It would be nice if you do this. But you don't say you must do this. And I'm
from a background where people will say, hey, you better do this, right? And but Jens was not doing it, and if I fail, I do revert back to X, but he didn't tell me that. Then Jens said, look, this is my training. I cannot order. I do suggest things. It's up to the grad student to do X or Y or X prime or Y prime. If they succeed, well and good. If they don't, they have learned something. It's worth it, right? And a very similar incident happened with me and my student Aman, who is sitting here on this thing. So we were working on a pretty complex problem, and then Aman picks up. We wanted to do something. Aman says, I want to do something more, right? So what is it he wanted to do? He said, look, in a compiler, you have optimizations and analysis. You keep doing optimizations, the analysis get outdated in a compiler. So you have to keep on recomputing the analysis. And the analysis writer need to know which optimizations may invalidate, or the optimization writer need to know which all analysis he has to invalidate. That's a painful work. So Aman said, I will automate this process. I said, look, Aman, it's an interesting idea, but it may be difficult, but it's up to you. In this case, he did not listen to me, and he came up with an excellent idea. So Jens, you are right. Sometimes not listening to your advisor is also a good idea, right? Yeah, so that's by the way, in case people are interested, on Thursday at 12 p.m., there's a talk Aman is giving on that. Here is one more story. This story, I thank Dennis, is he here? Yes, Dennis, for sharing it with me. I had forgotten this story more or less. So the story goes like this. One day, a man decides to go ice fishing. He goes out to his favorite patch of ice and begins drilling. And boom comes the voice, there are no fish here. He goes to another place, starts digging again. Again the voice repeats, there are no fish here, right? He's kind of slightly bewildered, something is happening. Then he says, once more, okay? He tries, goes some more, again starts digging. Booming voice, no fish here. He asks, are you God? Out comes the reply, no, I am the arena manager. Right? So many times I have found that we overthink, we try to overcomplicate the problem, and we are kind of going everywhere but to the solution. A similar problem we had was this analysis and Java context. We said we have the class files. You do this analysis result, analyze and keep the analysis results offline. Bring it to another place. But on the remote place where I'm running the Java code, there is a way to verify. But how do I verify the analysis? How do I trust it? We tried tons of things and failed royally. Then we found out that we have to think simpler. And then came the very nice result of what we call as ART, where the analysis writer can not only give you the analysis, but also give you a proof. You can carry the proof of the analysis, reuse it, rebuild the full analysis without loss of any precision, right? So this, if you are interested, if the people are interested, they can listen to it on Friday at 11:40, right? Here are a couple of smaller quotes before I wind up. So Jens had, most of these quotes are related to teaching. And the first one, he said, this is the usual thing in US where the deals you get are not what you want. I actually feel when I talk to my students, I don't know if it's still here in US similar or not in India. Students are, I deserve better grade. I deserve more marks. I deserve more, right? So my thing here is, this is a usual thing in higher education. The grade you get is not necessarily what you want, but what you deserve. So there is one more. This is something that today someone, I think Ben already has quoted. There's a fine line between meanness and evilry. Meanness is for midterm, evilry is for the final. There's absolutely no shortcuts to learning, right? I mean, for all the students here and those who want to kind of follow Jens's line, if you want to learn, the only way is to actually do it, right? The last one, students think they can get away with cheating because professors are too lazy to take it to the dean of students. What they don't realize that that is Jens, enjoys it too much not to take it to the dean of students. So this is about plagiarism. People copy happily and with pretty much nonchalance, thinking that it won't be reported. And to me, one thing that I kind of took away from interaction with Jens is that not catching them or not kind of reporting them is basically doing a disservice to the honest people. The people who have done real hard work, they get really impacted. Yes, and I'll wind up. So there is this very nice sloka that we have in Sanskrit that people may not follow, but here is the summary of that. And here is my haiku plus one. The reason why I call it haiku plus one is it has one plus one in all of those. So Jens, this is personally to you that there is a lot to learn from you. But yeah, I have, I guess, very little time. But I don't think you have ever taught us to give up. Like Mohsin said, it's not a short-term game, it's a long-term game. So one day, we will. Thank you, Jens, for everything.
So next up. So next up we have Dennis Brylo, who's a professor at Marquette. Dennis is a good friend of mine. I think I made friends with Dennis because he was the senior graduate student in the lab when I was an undergrad. And Dennis is a big lover of bad sci-fi, which he passed on to the rest of us. I don't think you realize, Jens, how much camaraderie there was at Purdue and how great the group was. And just having the lab and having Tony and Jan and all the students together, you can remember some of the movies that we watched, and we drank alcohol too. We played RISC. You remember that? We played Axis and Allies. Jens had a very funny strategy for Axis and Allies that didn't work out so well. And that was mostly at Dennis's place. And so Dennis was kind of like the social, he really kind of ran the social life of the Purdue lab. And that was so wonderful. So.
You know you're in trouble if I'm the social chair.
Yeah. I mean, does he look social?
But in the kingdom of the blind, from what I've Well, I didn't actually have a title in time for the program, but it was going to come out something like this. So on the general topic of Jens's legacy, we have heard from his many students who are doing things ranging from cybersecurity to type theory to destroying the universe. So I thought I'd talk a little about what I've been doing. So I was Jens's first PhD student. Circa 1997 at Purdue University. I was not the first to finish, but I was the first to start with him. Tian Zhao got that. He beat me. I was bitter about that. But so when I first began with Jens, he had no established lab group. And the advice that you always give to PhD students looking for an advisor is talk to their existing students and make sure that they're not insane. And the word on the street was, this guy's insane. Do not go work for him. My first day of CS 565, graduate level programming languages, 55 graduate students in the room. Jens walked in and he said, in the past, there have been several A's in this class. That will not happen this semester. Now, those of us who know Jens know that he often has a very dry sense of humor, and as I once heard him remark, I do not feel like I need to laugh or smirk to indicate to people that I'm telling a joke. And so he terrified an entire cohort of doctoral students at Purdue, that very first class. Later that same semester, when he gave the midterm exam, he required us all to go in individually to pick up our exams. You had to have a one-on-one appointment with Jens in his office. And I went in, and I had earned a 17 out of 100 on the exam. And I sat down and Jens said, 17, that's very good. And so I figured, okay, I'm in, right? So I became Jens's first PhD student. This is the Memorial Gymnasium at Purdue University, which housed the computer science department for many years. And you could tell that Jens was moving up in the world in computer science because he had the corner, it's off the side. I couldn't find a picture that had his office here. But his office actually had a window about this big, which in Purdue computer science, that was a very high status symbol. What you wouldn't know from the outside is all those windows are fake. It was a gymnasium. They remodeled the inside, so literally most of the professors' offices had no windows. And so that's brought on my lifelong fear of windows, I think. But so Purdue was good, and I did my dissertation work in static analysis of interrupt-driven programs. And when I told Jens I wasn't taking the job at the R1 Research University to go to Marquette University, I know he was disappointed. But I had the opportunity to get on the ground floor to build a computer science department that I just could not pass up. At the time, Marquette was just starting to hire PhDs in computer science in their existing blended math, stats, and computer science department. So I was in the first wave coming in, and they were basically offering me the opportunity to build a program. And I could not turn that down. It is the largest private university in Wisconsin. Those of you who aren't familiar, it's in downtown Milwaukee. It has like 13,000 students. And yet I think it said a lot about my colleagues and friends at Purdue that they all said, oh, so you're going to a small teaching school. No, there is a gradation below R1, it turns out, but that's not important. So Marquette's gone very well for me. Just to brag about me, 20 years later, you know, we're doing very well. I am now the department chair of a separate computer science department, about 16 faculty. Our growth has been phenomenal. For one brief shining moment last year, we were the largest doctoral program on campus, and we're still regularly in contention with the large programs. Things are going very, very well for us. And you know, Jens has also given me a pathological love of rankings, even though they can be easily gamed. But you know, I love the numbers. They come out, and it's like, ooh, where are we? It's just fantastic, right? With well-established strengths in a number of areas. And I have really focused on computer science education since earning tenure at Marquette, because it turns out that was a big problem we needed to solve. I've brought a lot of the best things that I've learned from the best professors that I had at Marquette in order to build a program that's very hands-on. And you saw some of my students' work earlier on. These problems are never done, right? There's always more hardware to build, more device drivers that need to be written, more, you know, multi-core additions we can make to our undergraduate courses. And what I really love about being at Marquette is the opportunity to take things that were reserved for only the PhD students at Purdue and to bring them down and run our undergraduates through that kind of challenging hands-on system building content. And so I've spent a lot of time doing that. But Jens, in a moment of rare philosophical musing, once said to me, you know, the thing about having a bunch of smart people around with really theoretical topics is that in the sudden emergence of a real crisis, you have them to do something really impactful and important. Now, at the time, I think he was trying to make the case for why I should go into type theory. But we were not building atomic bombs. Nevertheless, what I took it to mean was it was really important to use all the problem-solving skills that we had been given and to look for opportunities to apply them to really impactful problems in the world. So here I am at Marquette, circa 2010. And I had just earned tenure, and we were, like many computer science programs around the country, experiencing this sharp decline in the number of students coming into the program. At one point, we were canceling required courses because we had less than 10 students in them in the computer science major at Marquette. And I've already told you the end, right? It turns out all great 14 years later. But there was this really big problem, and no one seemed to really know what to do about it. And you know, we have astonishingly poor diversity in our computer science programs, across the country. A decreasing number of schools in Wisconsin were even offering advanced placement computer science. So we look at all these students coming out of the high school system, they don't even know what our field is, much less pick it as a major in many cases, right? And so the majority of school districts in our state weren't even offering this pathway. And of course, this is exactly why students were not majoring these kinds of fields, right? And so I put on my Manhattan Project hat and thought, well, I should start digging into this problem and trying to figure out what's really going on here and what can the computer science department at Marquette to try to do something about this. So there's all kinds of factoids in here about the way teacher licensing worked. I did this crash course in figuring out how we prepare teachers to actually go into high school and teach computer science. If you don't know much about this, stay away. It's a mess. It's really kind of terrifying, in fact. But there's this whole licensing issue, and individual teachers are rolling all their own curriculum and have very little support structures. Unlike almost everything that we teach at the high school level, a computer science teacher is almost always the only one teaching that topic in their high school, possibly the only one in their entire county. And so they can't even go down the hall and share resources. There's no community, or was not any community built up at the time. Right? So at the time that I started digging into this, there was only 31 Wisconsin school districts offering advanced placement computer science A, and that's with more than 600 high schools in the state, right? And so the numbers were not looking good. Moreover, a huge number of the existing teachers had basically been grandfathered in during the 80s and 90s, and we weren't producing more of them at anything like the rate that we needed. And in fact, while we were doing this census, 2 more dropped off the map during retirement. And I was like, oh my goodness, at the rate this is going, there's going to be no computer science teachers left. So I decided to do something about that, and have spent the last 15 years basically working towards this project. And this is about the time that Jan Cooney at National Science Foundation was going around to anyone that would listen to her saying, we have a big existential problem here in computer science. We need to build 10,000 more teachers for 10,000 high schools by 2015, or this whole new advanced placement computer science principles exam is going to fall flat on its face, right? I was like, okay, well, how hard could it be to get one of those grants? Hard, it turned out. It took me 3 years, but once you get one, it's not so hard to build up a little bit of momentum. So my time at Marquette has been mostly marked by my research program bringing in these large dollar grants that, I mean, it sounds impressive, but all the dollars go to paying teachers to come to professional development workshops, right? You'd be surprised how fast you can spend $1 million on teacher workshops for teachers that have essentially no background in computer science and have just been told, you're going to teach a year-long advanced placement computer science course. Hop to it, right?
No travel funds.
Yes, and there's no travel funds, and there's no support from the state, right? And so these grants coming from the federal government are essentially the only lifeline for these hundreds of teachers all over the state, right? So, and then there's all kinds of other things that come out of that as a result. National Science Foundation has been very good to me. So, what's the result of all this? Well, we actually approved K-12 computer science academic standards in 2017, and I was the co-chair of the standards writing committee. If you don't know how that process works, it involves education policy and state government and testifying in front of the state legislature and listening sessions and, oh my goodness, all kinds of things that had nothing to do with programming languages. But Jens once told me, you know, I cannot be intimidated by a handful of Greek letters in a paper. And what I took from that is, there is no problem that you can face that you cannot dig into and analyze and model and be able to come up with some kind of better understanding of the system. And so I dived in. And it turns out academic standards are a key barrier to colleges having pre-teacher certification programs to produce more academic majors who will then become computer science teachers. And it has all kinds of things to do with the way allocation of funding happens in the state. We've trained over 2,400 elementary school teachers to teach computer science in Wisconsin, reaching more than 150,000 at this point elementary school students in the state. You can start planting high school computer science teachers all over the place, but if students have never had exposure to computer science in elementary or middle school, they will not sign up for those courses. So you have to scaffold it back through elementary school and middle school, and you have to prepare those teachers as well. And so we've built this
large pipeline for running workshops at Marquette and Milwaukee and in locations all around the state to bring teachers in, almost all of them teachers with background in some other subject, often math or business or social studies or history, and teach them enough computer science, well, to be dangerous, frankly. But that's all we need to do to give students a taste of this and to get them thinking about future pathways that yes, sir?
Do I understand correctly that it was 30 AP teachers and now there's like 110?
Oh, no, we doubled it in the first grant by 2016. Now there's hundreds of them.
Okay.
Yeah.
So out of the 600 high schools, you said you are like way up in percentage.
Yes, we have more than 60% of the high schools in Wisconsin now offer a computer science course. So the impact, now I can't take credit for all of that, but I will. So, no, that's many other factors, but it is very gratifying to have people point to Marquette and say that we led the way in this effort in our state, and that's one of the things we are now renowned for. And when a student steps into one of those high school computer science teachers' AP classrooms and says, you know, I think I might like to study this, I know that Marquette University will be one of the first schools that is named by that teacher when they're having that conversation. And so that, you know, has created a very virtuous cycle for us. Milwaukee Public Schools is the largest school district in Wisconsin, 76,000 school children, 30+ high schools. It's right there in downtown Milwaukee. It's where Marquette's located. So a lot of our effort over the past several grants is focused in trying to build the pathways in Milwaukee Public Schools. Prior to our efforts, there had not been at any of those 30 high schools a single advanced placement computer science teacher in 10 years. Right? And this is a case that plays out in many urban areas, right? The computer science teachers are in the totally most obvious place, the white affluent suburbs ringed around the metropolitan areas. They're not in the rural areas, they're not in the small towns, they're not in the inner city schools, right? So we've been busy on that, and we build lots of partnerships and run workshops all over the state. And we're very agnostic about working with all different kinds of curriculum providers. And the biggest thing is that we've been able to build an actual professional organization, the Computer Science Teachers Association Wisconsin Dairyland chapter, which provides that kind of scaffolding that teachers were not getting. So when new teachers come into the pipeline, they have resources, they have people that they can ask for questions. Our mailing list is the envy of many of our neighboring states. There are people who lurk just to see how that community is working in Wisconsin as a result of some of this work. And there's a whole pathway of things that we teach and all these different workshops that we run. It turns out it's really a very complicated system with a lot of moving parts. And if you want to have lasting impact, well, allocate about 15 years and more or less $10 million. And that's the recipe for success. Teacher production is still really awful. You know, Wisconsin's still producing about, on average, 2 new licensed computer science teachers per year out of the university system. So the incentives just aren't there, right? If you have a student who's an undergraduate and they're double majoring in education and computer science, and they have enough computer science knowledge to become a computer science teacher and to get that license, they also have enough knowledge to get a job in computer science, which will pay 3 times as much. That's what they're going to pick, unless they're the rare unicorn, right? So most of our programming has been focused on training up existing in-service teachers whose degree is not in computer science, it's in some other subject area. They've already discovered their passion is teaching, and they are the advocates for their schools. So we dream of a day where undergraduate programs are producing hordes of new computer science teachers flooding out into the community, but the cavalry's not coming right now. So we need to focus on more practical problems to get through this. It's still the case that all this training still has diminishing returns for actually reaching the students that we want to reach. You know, the participation level in AP level computer science remains sharply tilted. I don't know if you've looked these figures up. We are the worst of all the advanced placement exams that are offered by the College Board. The gender balance in computer science is by far the worst. Worse than AP physics, electricity, and magnetism, my friends. So we have a lot of work to do. CS Principles has helped a lot, but there's still a lot to do. You know, it's important. And still, after all of this and all that teacher professional development, less than 5% of Wisconsin high school students still actually take a computer science course. And these numbers are on par with most of the other states. There's only 2 states out of the 50 in the US that actually have a requirement for high school students to take some kind of computer science experience. Most of the rest leave it up to the students, and as a result, they choose other things.
You brought it up to 5 and 7. It must have been terrible.
Yeah, it was really terrible before we started, right? I mean, this is the thing. I get to claim I more than doubled the number of computer science teachers in Wisconsin. And if you don't know that the starting number was 32, that sounds very impressive, right? But yes, it's when the numbers start so terrible. So now I lead the Pisces lab group. Ooh, promoting innovative systems for computing education in schools. Did I get that right, guys? Yeah, okay. Still working on the new acronym. But now I have my own doctoral students and master's students and undergraduate researchers that are working on designing new CS curriculum, software, and hardware that help enhance student learning in computer science, ranging from kindergarten all the way up through high school and on to undergraduate level stuff that we do. Training new teachers of computer science, working on that pipeline, all the big system challenges around policy and funding and licensing that need to be unraveled, and then actually measuring whether any of these implementations actually impact what students have learned, and measuring teachers' attitudes and beliefs about computer science, which turn out to be really important gateways to what they actually do in practice in the classroom. And this is not at all what Jens trained me for, and yet I feel like one of those Manhattan Project scientists that was just in the wrong place at the wrong time for a really important crisis to come along, and to recognize, oh no, it's me. I've become the expert on this in Wisconsin. I'm the one who knows the most about this problem and who's actually doing something about that. And that is a story that I've heard repeated in different forms from many of Jens's other alumni. So well done, and thank you for putting me in the position to have that kind of legacy. I doubt you will have questions about anything that I have just said, but yes, sir. Thank you. Yes, we should not underestimate the impact of those, right? Students who take a high school computer science course, much more likely to then go on to study it, right? So we got to build the pipeline. Yes, Julia.
So I didn't know high school computer science. So I had no high school in computer science. All my computer science was in middle school. So is there anything, are there any efforts?
Oh yes, I breezed through several of those slides, but yes, we've trained hundreds of middle school teachers around computer science programs, both standalone computer science and integrating computer science into existing middle school topics. And actually, several of my students in back are funded off a grant working on elementary school computer science integration. Usually they don't do it standalone. We have to integrate the computing into some existing elementary school topic, which is more challenging, but also really rewarding and a lot of fun. Okay, I think we're probably,
Dennis, it's just wonderful. There's this thing about who's teaching the teachers, and I realized that this is not about producing new teachers, it's actually teaching the teachers.
Yeah.
And teaching them to teach something new.
Yeah.
And from Denmark, in Denmark where I come from, all teachers are supposed to be able to teach 2 topics. And the ones you have, maybe they go through your program, maybe they're teaching 1 or 2, and you give them a second or a third.
yes, this is usually a 3rd topic for them in many cases. Yeah.
Very
Yeah.
cool.
Yeah.
I think this is very much about addressing the real problem instead of taking on the impossible problem, but making progress where progress can be made.
Yeah.
Well, for $10 million, but still.
Yes, exactly. All right, thank you all.
And we're going to have audience participation, which requires, so who's got the mic now? Do you have the lav mic? Is it here? Where's the lav mic? Yes. You need to give that to Jens, because Jens is going to participate in this. You will get this mic. Yeah, the mic is for.
No, that once this is okay, all right.
get your slides up?
So, maybe you could give the mic to someone?
Yeah, so I'm going to do the first.
Oh, I see.
Pass this mic.
I see, okay. Yeah. Do you want me to say anything, or?
The audience. What kind of mic setup do you want?
It's working.
I'm going to pass this mic around the audience. He's going to keep that mic. She's going to have this mic. Okay, so it's all good.
I have nothing to say.
Okay. And so B is Jens.
No, Jens is Jens.
Jens is Jens. Who are B? A, B?
Nobody. Anyone. It just goes around.
Okay. Got it. It's now.
Yeah.
It's no longer remote. Oh, it's no longer. We're good.
Yes.
Okay, so I think we're ready. Basically, Jens must participate in this, and that's why he has a mic. And the way this works is there are lines that you can see on the slide. Every line is read by a different audience member. And I will start, and I will pass the mic to the next audience member, who will say the next line. And we ignore the A, B labels. That's how it works. And Julia does not say anything, apparently. Does that sound good? Everyone understand? You get the microphone, you read the next line. That's it. All right, so we ready to go? A, brightly. This is a talk about summations.
Summations?
Yes, summations. Like the big sigma in discrete mathematics?
Like the big sigma in discrete mathematics?
You mean like the formula $\sum underscore I equal 1 power x fi equal f0 plus f1 plus \c dot plus fx dollar question mark?
Yes.
But it's not a formula. Beg pardon?
It is the representation of a formula.
In LaTeX.
Monsieur Magritte, thanks for coming by.
Oh, Monsieur Magritte, thanks for coming by. Ah, thanks.
Okay, thank you too, and congrats. Great to be here.
You are most welcome. Quick question, a summation, is it represented with a for loop?
Yes, it is. For example, here is the representation of the sum in NCC. It goes as a return type integer, foo argument type integer x, in sum equals 0, for loop with I equals 0 goes to I less than x, I plus plus, and then sum plus equals f of I, and we return sum. If f is the constant function that returns 1, the result is x plus 1 for any given non-negative x.
Thank you. And this talk is about nested summations?
No, I think it should be you.
Nested summations, yes, like $\sum, I can't read that. I equals 0 to the power of x, \sum, j equals 0 to the power of y, f of I, j, $period. I think the labels don't matter other than the person who read the title.
So they're implemented with nested for loops? No. Int bar, int x, int y, int sum is equal to 0 for I is 0 less than x, I plus plus for I is equal to 0, I less than or equal to y, j plus plus, sum plus is equal to f of ij, return sum.
So for any given non-negative x and y, if f is the constant function and returns 1, the result is x plus 1 times y plus 1.
Beg your pardon?
Well, yes, the result of this inner sum, $sign slash sum underscore classes. Well, everyone can read the code. Is that 1?
is 1 added y plus 1 times. So it is y plus 1 for any given non-negative y.
So the result of the outer sum 0 to x, y plus 1, is y plus 1 added x plus 1 times. And so it is x plus 1 times y plus 1. And for any given non-negative x and y, I see.
The inner sum implements addition as iterated incrementation, and the outer sum implements multiplication as iterated addition.
Professor Church, thanks for coming by.
Oh God, I'm getting a block of code. Quick observation, we could nest the summations even more. You are most welcome? No.
Thank you.
Thank you too, and congrats. Great to be here.
You are most welcome. Quick observation. We can nest the summations even more. Look, $sum underscore I1 equals 0 to the power of x, \sum I2 equals 0 to x, \sum I3 equals 0 to x, 1.
Just a sec. Int BAZ int x int sum equals to 0 for int L I1 equals to 0 and I1 less than or equal to x and I1 plus plus, and the second for loop int I2 equals to 0, I2 less than or equal to x and I2 plus plus, and for third loop int I3 equals to 0, I3 less than or less than or equal to x and I3 plus plus, and sum plus equal to 1, return sum.
So the result is x plus 1 to the power of 3 for any given non-negative x?
Yes, exponentiation is implemented as iterated multiplication.
Right, nest 3 sums, exponentiate with 3.
And nest 4 sums exponentiated with 4.
So how do we implement $ and $ nested sums so that we can compute $ parenthesis x plus 1 right paren to the power of n $question mark?
Well, n should be a parameter, just like x.
Or we implement it with an outer for loop? No, wait, that won't work.
We need a metaphor loop?
Or we could implement the nesting recursively, considering that it is defined inductively.
We could do that too.
Students are hereby drafted. Just read the line. Okay, I think we're going to wrap around. We're going to do modular arithmetic. Is it me now? This code? Oh, God. Okay, let me try. Int compute e, int x, int n. Curly braces are silent. Comments are silent. If n equals 0, return 1. Else int sum equals 0. For int I equals 0. I is less than or equal to x, I plus plus. Sum plus equals compute e of x, n minus 1. Comments are silent. Return sum.
So, for any non-negative x and n, we get x plus 1 power n if we nest n summations from 0 to x, with 1 as the body of the inner sum.
And we get x to the power of n if we nest n summations from 1 to x.
Which is not a good idea. For indexing, better start with 0.
Professor Dijkstra, thank you for coming by.
Thank you too, and congrats. Great to be here.
You're most welcome.
Quick question.
What if you put decreasing natural numbers as the successive upper bounds?
Let me try. Int compute f int x. You said that comments are. Sorry.
It's up to you.
X is the upper bound for sum. If x equals 0, return 1. Else it's sum equal 1 for int I equals 0, I less than x, I plus plus, sum plus equal, compute fx minus 1. Recursive call on a decreasing argument, return sum.
Oh, we get x plus 1 factorial, a factorial number for any given non-negative x.
Ah, right. Now we multiply decreasing natural numbers.
So that's the point of the paper?
The point of the paper is to make the upper bound of an inner sum depend on the index of an outer sum.
Can you give a simple example? We only have 20 minutes here.
I think 20 some.
You read that.
Fourth ball. Am I the fourth ball?
Yes, you're the fourth ball.
You're right, only 20 minutes. So here is the simplest example. The outer upper bound is the given x, and each of the inner upper bounds is the current index. Look. Sum of all these things, dot, dot, dot. Slash sum underscore curly brace I. Can someone format this, please? Sum of I1 equals 0 of x. Sum of I2 equals 0, I1. Sum of I3 equals 0 to I2. And so on up to sum of IN equals 0 up to IN minus 1 of 1.
Okay. Yeah. Well,
Okay, and the result is?
It is $C open parens x plus n comma n close parens $, a binomial coefficient.
A binomial coefficient, and you know that how?
Well, we test it first, of course, and then we prove it by induction using the Coq proof assistant.
Oh, I see. Do you have another simple example?
I get the easy part. Of course. Of course! Instead of the current I as the upper bound, pick I plus 1.
Let me try. Int compute C, int j, int n, where j is the upper bound of the sum when n greater than 0. If n equals 0, then return 1. Else int sum equals 0 for int I equals 0, I less than or equal to j, I plus plus. Sum plus equal, compute C, I plus 1, n minus 1, and return sum. Oh, thank goodness.
Okay, and the result is?
A Catalan number.
I see.
And here is what the paper is really about. Picking $1 minus I as the upper bound.
Why not?
Let me try. Int compute f int I int if n equals 0, return 1. Else int sum equals 0. For int I equals 0, I less than j, I plus plus. Sum is plus equal. Compute f 1 minus I n minus 1. Semicolon. Return sum. Semicolon.
And the result is?
A Fibonacci number. A Fibonacci number, and you know that how?
Same. Testing and then proving. The whole paper is formalizing.
By the way, these nested sums, where do they come from?
Mosner's theorem.
Mosner's theorem.
It's a really cool construction of streams of successive powers in their book of numbers.
Sorry.
But there are no streams here, just sums.
Right, as it happens, Mosner's theorem hinges on dynamic programming where streams contain intermediate results that are computed only once. Remove dynamic programming, you get nested sums. It's good fun.
So the paper is about Fibonacci numbers as nested summations?
Got an easier one this time. You want to try it? Okay, I guess we'll do modular arithmetic again, resetting. So the paper is about Fibonacci numbers as nested summations. Question mark?
Where are we? Oh, yes, and Fibonacci-like numbers such as Lucas numbers, which start with 2 instead of starting with 0.
I see that there are also Jacob-style numbers.
Yes, and Jacob-style Lucas numbers too, which start with 2 instead of starting with 0.
What a lot of induction proofs. Hey, big ones too.
Time out, guys.
Ouch, I'm broken.
Okay, so to sum up.
Time out. You can't add anything.
Okay.
Thank you everyone for the excellent talk. So the very last item of the day is reserved for the man himself. He's prepared some words. There's no limit to my gratitude.
Is there a limit to my speaking time? So I think I can just use this microphone. Thank you all for being here. I'm grateful to particularly to the organizers. Maybe that's many of you, but certainly Ben and Mayo and Fernando, who's back in Brazil. I had fun today, and I'm just deeply moved you're doing this, and I'm particularly moved that my own PhD advisor, Peter Masters, showed up. It's just fantastic. I'm grateful for all the time we spent together, and today I just want to ask myself the question: what did I learn all these years? And so I do have some advice that I've sort of kind of applied to myself also, and I'll tell you some things I'm proud of. I'll tell you some advice, and then I'll just tell you a couple of stories from business school. Now that we're at it, so let me just begin by saying, my parents, if you are listening online, hi mor far. To my family in Denmark, I'm thinking of you, and we are a few people in the U.S. from my family. There's my brother here in Los Angeles. There's my cousin in Iowa, and another cousin's daughter who's at Harvard at the moment for a visit. And then, of course, there's my wife, Tong, sitting over there. Maybe I should tell some stories about Tong. But there's also my son, who is a student at Cornell, majoring in computer science at the moment. And with some luck, he's also listening. It's just been a joy being married to Tong for many years. So not only am I very happily married, but she's also sort of my lucky charm. So I'll give an example. Christian Grothoff and his wife came to visit us for a few days, and we drive down to the beach on a day of a beach volleyball tournament, and we find a spot to park, no problem. It's always like that driving with Tong. We always find a parking spot. And then there's my son. He's one of the things I'm proud of. He's a member of the Glee Club at Cornell, which is the men's choir. And
it's very convenient because Coccinelle does a lot of streaming of the Glee Club performances. So Tong and I can go and watch our son online every once in a while to see how he's doing. And also, he is the webmaster of the Glee Club. And as just to tell you, they have a very good address. They are gleeclub.com. So it's not just a Glee Club, it is the Glee Club. So maybe enough about my family. So I want to say that, as a professor, I think our job, all of us as professors who are professors here, our job is to educate students who are better than us. And so at least I want to point out one thing I'm proud of with you. I'm sort of proud of so many things about all of you. I look around at my former students and I think, oh, there's a person who is better than me in this dimension. Here's a person who's better than me in this dimension. But I just want to highlight both Dennis Breilau and Krishna are department chairs. And I'm pretty sure better department chair than I ever was. And so it gives me a lot of pride that there are people who are also following in my footstep and trying to do better than I did in that dimension. Some things I'm proud of. I'm going to make it sound like I have both an award for research, an award for teaching, and an award for service. I actually have a research award for a distinguished paper in PLDI, which was about quantum computing. And that brings me to a story about POPL'24 in Boston. I had been studying, I started kind of to learn quantum computing in 2018. We get to POPL'24, and I get email. So it was actually one of these conferences where there was no time to go. I had decided to go home Thursday evening, and then I realized that all the quantum papers are Friday, so I changed my ticket to Friday evening. It's all good, and then next day after buying that ticket, I get email from a very famous person in the community saying, we're going to have these overview sessions in the morning so that newcomers can go and learn about the area before attending the session. And I've been tasked to find somebody who can give the overview session for quantum. Please, could you do it? And I was thinking, this is fantastic. There's this senior member who thinks I'm good at quantum computing. And so I wrote back and said, sure, I will do it. I actually just changed my ticket so that I can be there. It's all great. And the story doesn't end there, because the next email I get says, thank you, thank you, thank you. You totally made my day. I had asked all the experts on quantum computing, and none of them could make it. So I actually also got a teaching award. What I did was that I got Tony Hosking's slides from his compiler course at Purdue, and then I was teaching that course for a long time. In fact, I still use some of the slides to this day. But I actually ended up getting a teaching award, in some sense, for Tony's course back then, which I'm very proud of. And then last year, I got a teaching award for my courses on quantum computing at UCLA. And so to me, those are sort of really highlights. I still try to do a good job of teaching, sort of notwithstanding all the jokes about midterms and finals and so on. And indeed, when I got this teaching award at UCLA, both Tong and John, my son, were there, which was an absolute highlight of my life, like today is. I also got a Distinguished Service Award from SIGPlan, which is something that really sort of matters a lot to me, because SIGPlan is like my intellectual home, and I see many SIGPlan members sitting here. And I was just sort of thinking for a moment about what I did with all this service that people claim today that I've done. So I was department chair for 5 years, and I remember the highlight of that as that we were getting a new building. And there was this thing about pitching for people to actually want to go to the new building. And I found out, maybe too late, but I found out really what the main pitch was, which is that we designed the building so that all professors had windows, all the labs where the students were had huge windows. And I'm happy to say that Todd and I and more people are sharing one of those labs today, and I think it's very good. But there was a pitch to make there. Then I became SIGPlan chair a little bit later, and we had a problem. So for many years, many of you will remember Annabelle was our conference manager who did an outstanding job for us, maybe like above outstanding. And then just before the pandemic, as it were, changed her line of work from working for SIGPlan and whatever else she was doing to work for the government in the United Kingdom. And so we needed a new conference manager, which is like huge shoes to fill. We all loved Annabelle. That's the short story. And so I believe that one of the most important things I did for SIGPlan was to help hire Naringa, who is now running UPSLA, for example. and I think is doing a good job. Maybe it's just impossible to be Annabelle, but I don't think Neringa is Annabelle 2. She's like Neringa 1, and so I think she's really good. And so that's something there. Then I became, so you know that ACM has 38 special interest groups, of which SIGPlan is one. And there's a kind of a chair over that who's like the chair of all the special interest groups. So I was that for 4 years. And so I was kind of the pandemic chair, and then there was the pandemic ended. And there was this huge thing about how much overhead to ACM should the SIGs pay. And so that kind of became a big thing. And I think that a thing that I helped contribute there was to basically get this settled so that we could work out what the overhead should be and move forward. And today, all of this is like completely solved. But there was sort of a lot of politics there. And in many ways, I think of that effort as probably a bigger political effort than even department chair moving to a new building and so on. And now I'm, for the 5th year, I think, on the ACM Council, which is like the top deciding body of ACM. I'm a member of the council, and the next thing coming up is open access, and which will affect all of us. So ACM sort of made a promise to the members that if it's sustainable, we will change to open access, which means flip the entire digital library to open access by January 1st, 2026. That's a year and a little bit. And so that's a huge thing going on at the moment, which is like, it's a financial problem. It's a problem about how we all think about open access and all this. So that's something we are working on. And that's something I'm proud of being part of. It was actually, anyway, it's something that I think is really important for the community. I really believe in open access. And I think we should find a way to make it sustainable and make it happen. Okay, so now some things I've learned. I want to start with Peter Mosses. That's a very key piece of advice that I've taken with me, and I think that I've said to every single PhD student I've had, which is the question of what is good research. And the advice that I got is that good research has 3 components. It has to be new, it has to be interesting, and it has to be difficult. And of course, we can talk about what this means, but that's the yardstick I use to measure all research ideas and also kind of research outputs. And I think I see many nodding heads in the audience who have heard this advice from me. So I'm essentially just passing on Peter Mosses' advice. And I think it's just the right way of doing it. In all these years, I never came across better advice than that. And then I have still some advice of my own. I will just tell you my #1 advice, maybe not just for research, but in general, which is make progress every day. So I have had so many experiences with taking on problems that are just too big to think about, too big to do in a day, or too big to do in a month. And so what do? And I realized over time that the way to do it is to make progress every day. And I think the way I learned it was, well, I would actually say, in one way to sum up my whole career as a computer science person is to learn to do reviews faster, because there's so many papers to review. And so how do you learn to be faster? So of course, there are many ways. You can learn to read quicker, to take notes better, and all this. But there's a very important point when you have a big pile of papers, which is make sure that there's one fewer the next day, maybe more than one. But every day, make the to-do list a little smaller. That's how I feel good about, oh, I'm actually making progress. The next day, I look at the problem a little bit differently. This is how I keep myself mentally sane. ACM has a student newspaper, maybe you know, called Crossroads. And it just happened that the editor-in-chief was a UCLA student for the last while. And so she came to interview me, and she said, I just want the interview to be about your top 3 pieces of advice. And so there I was. And so I didn't give the one I just gave about make progress every day, but I gave 3 other ones that I'll just summarize. The first one is kind of what we're doing today, which is connect with many people. I strongly believe that we need to just be connected to as many people as I can. And there's a story that I've told, maybe again, all my students, I just want to repeat today. And that is that, so it's like you find yourself going to a cocktail party, you scan the room and you see 5 people that I will concentrate on. The first person is somebody you would give your left arm to talk to. The next person is somebody you would very, very, very much like to talk to. The third person is somebody you really, really would like to talk to. The fourth person is like, okay, maybe not that important, but still. And the fifth person is like really way down on the priority list. 10 years later, it will turn out that it is crucial you're connected to person number 5. This has happened to me so many times that it's not funny anymore. And it's just, I'm telling you, just please connect with person number 5. That's my message. Second point is plainly care about details. I don't need to tell you this, or you are detail-oriented people, but I think care about details in what I write, care about details in what I read, and it's enriching for me. It's like I somehow love details in a way, and that I find that it just enriches life. And then there's the third thing, which took me decades upon decades to learn, which is how to be productive. Figure out how to be productive. For me, I finally realized that I like these 2-hour work spans. It's like sit down, work intensely for 2 hours, and then take a break. And the way I do this, I drive to Starbucks, and then I sit for 2 hours, and then I come back. And at Starbucks, nobody can find me. And so it's really intense, closed off, and progress. But this is something I encourage everyone to think about. Find out how to be productive. And then realize what it is. I don't even understand why I'm productive at Starbucks, but it's like when I walk in, I become twice as efficient as I normally am. And it's like, I don't need to understand this, I just need to go with it. And so that's what I'm doing. I also want to say that I do make lots of mistakes, and I remember one time we were at UCLA, we just had a seminar, almost everybody had left, and this was in the old days where the overhead projectors up under the ceiling, and we had thrown away the remote control, and I wanted to be a good citizen and turn it off, and I go up on the table, and I make all the wrong moves, and I fall, and I had blood coming out of my arm in a 90-degree angle. And I'm happy to say that Christian Goldhoff stayed, and actually maybe a few more people were there, got me bandaged off, and Christian went with me in the ambulance 2 blocks down the road to the UCLA emergency room, and I remember we walked in, and there was like this huge crowd of people sitting there and waiting, and they took one look at me and said, "You're coming in." And so we got me fixed up, and it's all fine. But Christian, thank you for being there when I needed you most. So I think I'll just stop with all the lessons and just give a couple of fond memories. So the following may sound sort of a bit self-congratulatory, but I will tell you because I'm hoping to convey a message. So I applied to business school. I was finishing up as department chair. I thought I want to do something else. Key people in the community that I set highly, particularly Mads Tofte in Denmark, and my former dean at Purdue, went to business school sort of later in life, and I thought if they can do it, I can do it too. And so I applied, and I get an admission interview. And so I show up for the interview not knowing what's going on. We sit down, and they bombard me. Well, one person bombarded me with questions for an hour, and it was like I thought, okay. And then at some point, this person took this whole binder and sort of closed it, leaned back, and said, okay, one more question. And I thought, okay, so it's clear that now all this was just like, you know, beginning. Everything is in this last question. And then the person said, what does success mean to you? And I said, oh, that's easy. For me, success means that when I get up in the morning, I look forward to the day. And particularly what I look forward to is to work with you people, to my students, to my colleagues, and everybody. And I know that if I feel like this is what I want to do when I wake up in the morning, then I am successful. This is really where I want to be. I also want to tell one more story from business school, which is on my blog. So yes, I wrote a blog about business school. And so the following is something that has become quite meaningful to me, and I'm going to change the story just a little bit. So first semester, we have quarters at UCLA. First quarter, we have data analysis. That's just the statistics, right? And so the professor is Rakesh Sarin, wonderful guy. He gives us a very fine statistics class with an eye towards business, statistics class with an eye towards business. And then, so he'd be a final lecture. We're kind of closing the books on the class before final exam. And then he looks around and then he says, So you can imagine in my class, I was like the least qualified person there. CEOs, CFOs, COOs, people who own their own company. There's like full of those, and then there was just me who had just been department chair. Anyway, so he looks around and he says, you people juggle a lot of balls. Sometimes you drop a ball. That's okay. But one ball is a crystal ball, and that's your family and your friends and your former students. Don't drop that ball. And so I just want to say, in a way, thank you for not dropping me. Thank you for remembering me today. It's been a wonderful ride with all of you, and I can say that I'm remembering you, and it's you are a very meaningful part of my life. And I just want to say sort of how I keep organized. So it's actually true that I keep 5 diaries every day. So I just want to tell you, I write down everything. Actually, most importantly, every night I write down whether that day I have no emails in my inbox when I go to sleep. I've done that the longest. I write down everything I eat. I write down how many hours I put into work. I put in how many hours I go to the gym. That's the simplest diary to keep. And then I have one more diary, which is more like sort of observations. That is like nice. My son graduated from high school. I put that in. That's very nice. So I keep this every day, and I'll tell you why it's important, just in case somebody wants to be inspired. The one about writing down how much I work, it's very good, because sometimes I think, my goodness, I didn't do much last week. It's like, why did I waste last week? But then I can look back in my log and see, actually, I put in a lot of hours last week. Maybe I didn't make as much progress as I would like, but I really tried. And for me, that's actually enough to keep going and to not be too worried about life. So anyway, to my students, I'm proud of you. I'm happy we're still connected. Thank you for doing this. And thank you for your friendship, everybody. And I just want to tell you how perfect it is that this day is today. I don't think so many people know, but my lucky number is actually 2. And today is 10/22/2024. So 22, there are already 2 there. And 10, that's 2 in binary. So it's just perfect. So thank you, everybody.